Okay, so today we're going to be discussing hematology, talking about the blood. The word parts that are important to us in here are hemato, which means blood, as in the term hematology, logi being the study of. So hematology is the study of the blood. Okay. And other word parts important for us will be adding as we go. But you see a couple colors here, erythro, meaning red, and leuco, meaning white. That's so that we can name the blood cells, the red cells and the white cells. And I'm going to add something here. Cyto means cell. And examples of those word parts would be like erythrocyte, your red cells, and leukocyte, your white cells. Now, thrombo means blood clot, hence the term thrombocyte, your clotting cells. So that gives us the ability to now name the cells in our blood: erythrocytes, leukocytes, and thrombocytes. Okay, so those word parts being important for us today, and we will be adding some as we go. And we need to first say what the purpose of the blood is. What is it there for? Okay, a little bit of history on this is that back in the day, guys, when they were learning anatomy and first getting into cutting the human body open and seeing what that stuff is in there and all that, they didn't really understand that blood moved around inside the body. Their understanding was that the body was filled with blood, kind of like a container. And if you put a hole in the container, the fluid runs out. They didn't understand the concept of the blood being circulated around our body inside blood vessels. They just thought we were just a container filled with this red stuff. Yeah. So our understanding brings us, or our study and research has brought us to the level of understanding we have today. The blood does several things for us. Primarily transporting things around the body for us, like nutrients and oxygen. Oxygen is delivered throughout our body, kind of like a Amazon truck. It goes to the lungs being the warehouse, the Amazon warehouse, picking up the oxygen and then delivering it to every cell in the body. Once that delivery is made, returns to the warehouse, picks up more oxygen, back out to deliver to the cells again. So think of it like an Amazon truck, constantly going to the warehouse and then back for each delivery. But remember, in this sense, the Amazon truck is only delivering to one house, one cell, and then back to the warehouse and then back out to another cell. So the blood transports nutrients and oxygen for us that way, just moving back and forth, moving this stuff from the warehouse to the delivery point, back to the warehouse, pick up more to a new delivery point, and so on. The blood also regulates our body temperature for us. When a body part gets cold, we pump more blood into that part to warm it up. If you've ever seen a light-skinned person or a white person outside on a cold day, you might see their cheeks turn red. As their face gets cold, the circulatory system pumps more blood into their face. And that's why Santa Claus always had rosy cheeks. Increased circulation to warm up the face. Ladies probably know this, and guys may not realize this, but if you see a lady outside on a cold day in a dress, you wonder, aren't their legs cold? Well, usually not when you wear a coat, because the blood coming from the trunk of the body is warm. That pumps out to the legs and actually warms the legs up. Okay. And then circulates back up, warms up, back out, warms the legs. The same thing for those jackets that don't have sleeves on them. You know, you can be out as long as you keep the trunk of the body warm, the arms will be warmer than you would think. So we pump blood into areas that need it in order to warm up that body part when needed. The blood also provides immunity for us. Our white cells are what we refer to, or what we're talking about when we say your immune system. That is your blood cells. They fight off infection for us by destroying viruses, destroying bacteria, destroying infected cells, anything in our body that is an immune system problem for us. The white cells take care of that for us. So transporting nutrients, transporting oxygen, regulating our body temperature, and providing immunity. All right. The purposes of the blood. And you can see white in this image right here. We won't get into that. So anyway, the blood itself is liquid tissue. I know it sounds odd to say that if we haven't used that phrase before, liquid tissue, because anything that has living cells in it is tissue. And we just alluded that we have red cells, white cells. These are all living cells. They have a nuclei, they can reproduce, and so on. So that makes the blood liquid tissue. Our bones would be an example of hard tissue. They have living cells, but the tissue itself is hard. You'll know that if you ever break a bone, it hurts because there are living cells in there. But if you cut a hair, it doesn't hurt because that's dead cells. So anything that has living cells is tissue. Since blood has living cells, it is then liquid tissue. We have about 5 or 6 liters of blood in our body. The bigger you are, the more blood you might have. And then when we lose some of that blood through the process of hemorrhage, remember, hemo is blood, raj means bursting forth or flowing. So hemorrhage means blood flowing or bursting forth from your body. You have a hemorrhage. Hemorrhage can be internal or external. The blood is leaving out your body or it's not. Y'all may have heard of the term internal hemorrhage or bleeding inside. You can hold all your blood inside your body. Now, we need to remember that. Wait for the whiteboard. Here it comes in a minute. And, y'all know I need to use my whiteboard because that's just me. In the classroom, I fill the whiteboard at least 3 or 4 times per class. I haven't erased and start over again and so on. But anyway, it helps our visual learners. And since I'm a visual learner, it helps me to teach this way as well. All right, so you see your basic blood vessel with blood flowing through there. If that blood gets outside this vessel, it's no longer doing what it's supposed to be doing. So you can have a liter of blood out here and it's not doing anything for you. So you will die just as quickly as somebody who is losing this blood outside their body. Understand that this is still inside your body, like in your chest, in your stomach, in one of your legs. This blood is just pooling out there, but you're not bleeding. You don't see the blood gushing out of the person's body, but they're still bleeding to death. They just have an internal hemorrhage. Okay? So any blood that's not inside the blood vessel is not doing what it's supposed to be doing. And you can bleed to death and not lose a drop of blood. It's all getting pooling inside your body. All right. So that's an internal hemorrhage. The blood is not leaving the body, but it's not doing what it's supposed to do either. Either case, it can lead to death. All right, so where were we? Right here. All right. So a hemorrhage can be internal or external. If somebody loses more than 3 liters of blood, there's a good chance they won't survive that. And it's one of the things that paramedics look for when we show up at an accident site. We're looking to see how much blood is actually in the street. That's a big deal for us, okay? And it's hard sometimes, especially at night, because at night, you can't really tell whether it's blood or whether it's oil from the car or condensation from the fluids from the radiator or air conditioner or something like that. We have no idea what that liquid is in the street because it looks black. So you might see a paramedic at night with a flashlight looking at the street. Half the time they're looking to see if that liquid right there, is that blood or is that automotive fluids or whatever. Okay. One night I actually knelt down in some. I wasn't paying, well, I was paying attention, but I was kind of in a hurry. This was an instance where in Greece, they drive these things called a manoli cart. It's a three-wheeled car, if you will, or small little golf cart looking thing, but they drive them on the roads up and down the highways and stuff. And it's usually somebody delivering vegetables to the market or whatever. And you common sight is to see a little old man, little old lady sitting up on their manoli cart, one wheel in the front steering it like this, two wheels in the back, and they're headed down the highway. And we got a call one night for a truck had hit a manoli cart. When we got out there, the truck was sitting up on top of the cart. It was completely underneath the truck. And remember, they sit up on this thing like a covered wagon. There's no cab or anything. It's just them sitting up there. No windshield or anything. And the truck is sitting right up on top of this thing. It was nighttime, so I figured there was a little bit of rain going on. The street was a little wet. So I knelt down to look underneath the truck to try and see the two people. The man was dead, but I was trying to get a little further over to see the lady on the other side, and she was dead too. But when I stood up, my pants were wet, in the knees. So I figured, wow, I was kneeling in water, Got back to the emergency room, found out I'd been kneeling in blood the whole time. And yeah, it did soak through my pants, and you see blood on my skin and all that. This was back before some of the rules that we have today. As a matter of fact, when I started practice, guys, we didn't wear gloves. Now imagine that, how dumb that was. But it was the standard at that time. We didn't put gloves on. And as a result, anybody who's been practicing as long as I have had at least one of the hepatitis. For me, I've had hepatitis A. So anyway, that is, if you lose more than 3 liters of blood, most likely you're probably not going to survive that. Okay. All right. So anyway, blood is separated into parts, and we call those the blood components. And you should know these. Why aren't these in red? I think I did this back before I was turning everything red like that. Anything else we need in red? No, I think that's it so far. Oh, there's some red down there. Okay, maybe I saved it for down there. All right, so anyway, the components of blood. When we say what we mean is that the parts. Blood has 3 main parts. And the first one we have been talking about for a few seconds up on one of the earlier slides was the blood cells. The blood cells are known collectively as the formed elements. They're the things in the blood that have shape. If you look at blood under a microscope, you'll be able to see these things because they have a shape to them. So we call them the formed elements. And we'll be looking at each formed element as we go. So the first part of the blood is the blood cells themselves, the formed elements. Now you can take all the formed elements out of a blood sample, and it's pretty easy to do. If you, wait a minute, why wasn't I on this slide? Why did I change? Anyway, all right. So you can take the formed elements out of a blood sample pretty simply by using that machine in the picture right there. That's called a centrifuge. And what it does is take a blood sample that you insert in the tubes like this, and it spins them around. Has anybody ever been to amusement park and you get on that one ride, the one where you get inside this little barrel looking thing and you stand back against the wall and it starts spinning real fast and the floor drops and you're stuck to the wall? That's centrifugal force. heavy things get pulled to the outside. So when you put a blood sample in a centrifuge, it applies centrifugal force to it. The heaviest things in that blood sample gets pulled down to the bottom automatically. And the heaviest things in there are the blood cells. So when you put a blood sample in a centrifuge and spin it around, it's going to look like this when it comes out. That goes in, this comes out. All the heaviest stuff has been pulled to the bottom, and that's all your blood cells. And that's how simple it is to separate the formed elements from the rest of the blood sample. You put it in a centrifuge, spin it around for 15 minutes. All the heavy stuff get pulled down to the bottom, and then you have this stuff separated for you. So the blood cells are down here, and what you have up here is called your plasma. So it's really simple to separate blood components in a basic laboratory, and medical assistants are going to learn how to do this in your lab classes. Not important for PCTs to be able to do this, but medical assistants, it'll be part of your lab classes, how to separate a blood sample and pull the formed elements out or to the bottom, and the yellow looking stuff up above that is called plasma. Y'all have heard of plasma before, and the thing that's left in the plasma are the stuff that we call clotting proteins, the stuff that allows your blood to clot. We'll be talking about that a little bit more later in the class. So that's how you separate formed elements from the plasma. Put it in a centrifuge, spin it around for 15 minutes, take it out, everything will be separated. Now, these clotting proteins, these can also be removed from the sample if you are trying to get down to the simple liquid part of blood, the stuff we call serum. You're going to have to take the blood cells out, then you're going to have to take the clotting proteins out. Once these are removed, what you have left is called serum. And that's also really easy to do. It's easier to take the clotting proteins out than it is to take the formed elements out. What you want to do is take this blood sample, whole blood, put it in a centrifuge, spin it around for 15 minutes. It'll come out like this. Take this tube, set it on the counter for 45 minutes. While it sits there, the clotting cells down here will start to form clots, and all of the clotting proteins in here then are going to be used up to form those blood clots. So if you sit this on the counter for 45 minutes, all those clotting proteins are going to get used up. And you end up with strictly serum. So it's real easy to separate the blood components, spin it around, set it on the counter for 45 minutes, and what you're going to have left up here in the top is called serum. Serum is used primarily for vaccines and for research. There's not a big call to transfuse serum to somebody, but you know we transfuse plasma all the time for folks, and we'll be talking about why we do that, why we transfuse plasma without necessarily needing the formed elements in there. All right, so those are the three components of blood: the formed elements, known as our blood cells; the plasma, which still contains the clotting proteins. If you take the blood cells and the clotting proteins out, what you have left is called serum, the liquid part of water, or liquid part of blood. There is still some markers and that type of stuff in the serum, but no transfusible value. Put it in somebody else, used primarily for vaccines and research. So that's how you separate the three components of blood, and know what they are: the formed elements, the plasma, and the serum, the three components of blood. And then spinning it out. Okay, so we're going to talk about the formed elements first. We'll list them out, and then we'll talk about each one for a few minutes. And the first formed element is called your erythrocyte. Y'all remember from the first slide that erythro means red. Cyto means cell. The erythrocytes are your red blood cells, abbreviated as RBC. Now, if you're ever asked to list the formed elements, nobody wants to see you write red blood cells. We want you to use the real word. Erythrocyte is what you want to be using. So the erythrocytes are our red cells. Leukocyte. Leuko means white. So leuko, white, cyto, cell, your white blood cells, or WBCs. And the third formed element is called platelets. The technical term or the real term is thrombo, which means blood clot, and cyto meaning cell. These are your clotting cells. Their nickname is platelets. So those are our three formed elements: the erythrocytes, red blood cells; leukocyte, your white blood cells; and thrombocytes, your platelets, your clotting cells. Let me go on and put it like that. Your clotting cells, platelets. All right, so let me go on and do this morning. Nicole is here. Where's Jordan Carter? Jordan. No Jordan yet. Okay. Yordell is here. Michelle is here. Renisha, you here? Renisha, anywhere?
Yes, I'm here.
Okay, I see you. Thank you. Christopher is here. Cheryl is here. Cassie is here. Jennifer is here. Elena Guzman, there you are.
I'm here.
Davian is, I thought I saw you. There you are. Isaac is here. Jaime is here. Jasmine is here. Linda is here. Melissa Lucio is here. Tatiana is here. Maria is here. Vanessa Pargas, anywhere. I don't see you. Okay. Selena Puente. Do I see you anywhere? No, I don't see Selena. Okay. Latasha. It's Latasha. I'm starting to get a little worried about Latasha. Latasha Reed. Okay. And Sarah is here. Alma is here. Esther Torres. A little worried about Esther too. Esther, you here? I don't see you. Okay. Crystal Torino, and then Savannah Wilburn is here. All right, let me go on and send this email, and we'll get back to this here in a second. All right, so, wrong one. I do, no, what is today? 8/5. All right, speak up if you see your name on the list, please. Jordan Carter, Vanessa Pargas, Selena Puente, Latasha Reed, Esther Torres. Going once, going twice. Sent. All right. Oh shit! I should have seen that earlier. Forward that to D, so she'll see that. Okay. Anybody else? I'll look for that Jasmine here in a little bit. And then, okay. Okay, there's Selena. Okay, let me forward that one as well. All right. So remember, guys, I do like when you send me the email, let me know that you got some issues out there or whatever, so that I can let them know, so they don't be having to call everybody trying to find out where you are. All right. So anyway, the three formed elements: erythrocytes, leukocytes, and thrombocytes.
Mr. Malone.
Yes.
I need to take this call. Did you get my text? My dad had a stroke.
Oh, I'm sorry to hear that. Okay.
So can I just step out real quick? Okay, thank you.
You'll do what you got to do.
Okay.
All right. So the first formed element is that we're going to talk about is the erythrocyte, the red blood cell. And starting with the idea that this is the most numerous cell of the human body. We have more of these than every other cell combined. I know y'all have heard that we have billions of brain cells. Well, if you take those billions of brain cells and you add every other cell of the body together, you still have more red cells than that. The most numerous cell that we have. They're produced in our bone marrow, if you've ever wondered what that stuff does. The bone marrow is an area that's inside the bones. So this is a bone, and each end being the end of the bone. The area down the middle of that bone is where the bone marrow is. And in there, we produce all of our blood cells. The red cells are manufactured in there for a specific reason. Red cells cannot reproduce. As a result, they have to be constantly manufactured for us. Other cells in our body that have a nucleus and they have DNA in them, like a skin cell, you damage a skin cell, a new one is born right there in that area when the cell just splits. So if you cut your cell, a new cell gets produced right there at the area of the cut by cells just reproducing themselves. The red cells can't do that. They have no nucleus. As a result, they have to be constantly manufactured for us, and they're manufactured in our bone marrow. And we create them at a rate of approximately 2 million per second. So every second of your life, you're producing 2 million red cells being pushed out of your bone marrow every 2 seconds, or every second, 2 million. And whenever we transfuse bone marrow to somebody, it's for that reason. They're having some issue with producing blood cells for their body. So we transfuse bone marrow to them to bump up their production of blood cells. And primarily it's going to be their white cells that they have a problem with producing properly. So we transfuse a lot of bone marrow to people with the condition of leukemia. They're not producing enough white cells. So we transfuse them with somebody else's bone marrow and hope that kicks their bone marrow into overdrive and it starts producing enough cells for them. So whenever we're transfusing bone marrow to somebody, it's for the purpose of producing blood cells. So they come out of our bone marrow at about 2 million per second. The red cell has no nucleus, so it cannot reproduce. And that has to be constantly manufactured for us. Most numerous cell produced in the bone marrow, they have no nucleus, so they cannot reproduce. Now, the red cell will live for approximately 120 days. Now, this is all the cells of the body have a programmed lifespan. We kind of mentioned that yesterday, that's what getting old is. The cells don't reproduce at a appropriate rate like they should, and as a result, the body starts to break down as we get old. But our cells only live a programmed period of time. And for the red cell, that's 120 days. After about this time, the cell will start to degrade to the point that it can't do its job anymore. So our immune system will come along, identify the old red cells, and carry them into your spleen. That's where they are destroyed. So think of your bone marrow as being the automotive plant where the car is produced, and the spleen is the junkyard where the car goes to be destroyed. But that destruction is not just go in and destroy them, it actually deconstructs them. It takes them apart. The same way you do a car at a junkyard. You don't just destroy the thing, you take all the parts that are useful off and you keep those, and then you destroy what you don't need. So the red cells are deconstructed in the spleen. And the primary substance that we want to keep from that red cell is the iron. We never want to get rid of that stuff. So the iron is then transported to your liver, where it's stored until it's needed to produce new red cells for you. So the spleen deconstructs the red cell, primarily keeping the iron and another substance we'll be talking about later called heme. Both of these are saved and transported to your liver. Everything else is then destroyed. The iron and the heme are stripped off, sent to the liver. Everything else gets destroyed. And in the digestive system, we mentioned that the byproduct of that destruction is called bilirubin. The bilirubin is also transported to the liver, and then the liver puts that into your colon for you so that you can excrete it from the body. So I guess what I'm saying then is my first time actually saying it this way, is that everything from the red cell's destruction is sent to the liver. The iron, the heme are then both saved, and the bilirubin is excreted. So that's what your spleen does for you. Deconstructs these red cells. Now, since we produce red cells at about 2 million per second, we're actually destroying them at the same rate, about 2 million per second, to make sure we have a balance in the body. There is a such thing as having too many red cells. Okay? Makes your blood a little thicker than it should be. Makes the heart work a little bit harder. So the red cells live for approximately 120 days. Once they reach their programmed lifespan, a white cell will grab it and take it to the spleen, where it'll be deconstructed. The iron, the heme, and the bilirubin are all transported to the liver. The liver saves the iron and the heme and then excretes the bilirubin through the digestive tract. All right. So what's the purpose of the red cell? Boom, simply put, there it is. Carry oxygen. That's all it does. Carry oxygen. And how does it do that? Da, da, da. Oh, wait a minute. No, I didn't want to copy here. Undo that. Undo, undo, undo. All right. I don't know if I can do this. I haven't tried this before, so let's see. That no, that's paste right there. Oh, look, hey, it did work. Okay. As a matter of fact, I've done this before. But anyway, all right. So the red cell. We'll stop that. Think of it, boom, red cell with this thing inside there. That's why the red cell has no nucleus. On it. L-E. The right cell has no nucleus. There's no room for one. The space is taken up by this molecule, which is called heme. So if you look inside your basic red cell, instead of a nucleus, you're going to see this molecule in there. This twisted molecule of heme. Okay. Now, what's important about this molecule is these things right here. There are 4 of them. Referred to as bonding sites. And these bonding sites contain a very, very important mineral for us. That mineral is called iron. That's why iron is essential to humans' existence. It must be there for us to create the appropriate number of red cells and for the red cells to be able to do what they do. That's why the spleen doesn't excrete any iron. It goes straight to your liver and it's stored there until it's ready to be used. And remember that a little bit later on, that the iron is stored in the liver. All right. So the iron, what does it do? Each one of these bonding sites will pull in 1, 2 iron molecules attached to them. Or excuse me, oxygen molecules, because these have iron in them. Okay, let me take all this off, start over again. All right, so your bonding site right there contains iron. Essential for making the heme molecule is the iron. Now, what does the iron do for us and why is it there? Okay, have you ever left a tool out in the yard, a pair of pliers or a garden tool or something, and left it sitting in the yard for a couple of days? You finally find it, and what's it going to look like?
Rust.
It's going to be rusty. When something gets rusty, we call that oxidation. The tool has oxidized, meaning that oxygen molecules have attached themselves to the iron in that tool. So it's a natural occurring process. Oxygen is attracted to iron. So what is the iron for? When we send this red cell with the heme in it through an oxygen-rich environment, when it comes out, it's going to have oxygen molecules attached to it like that. That's all the red cell does. And what is a oxygen-rich environment in our bodies?
The lungs.
Your lungs. So you circulate a red cell through your lungs, When it comes out the other side, it's going to have oxygen attached to it. The oxygen attaches naturally to the iron. And now that red cell can be sent out to your tissues like a delivery truck to carry that oxygen to the tissues. And what do we use oxygen for? Remember, oxygen plus glucose equals energy. So that's why we need to transport that oxygen to the tissues, to our cells. The cells need it use it as energy. It attaches to the glucose in that cell and boom, the cell has the energy to do what it needs to do. Whether it's fight off an infection or produce a hormone in your body or contract a muscle, whatever that cell does, it now has the energy to do it. So the red cells are the delivery trucks for oxygen. That's all they do in their entire life. They go to the lungs, the warehouse, fill up with oxygen molecules, get pumped out to your fingertip, drop those molecules off, and then back to the lungs to pick up more their entire life for 120 days. Now, when heme, this substance right here, has oxygen molecules bound to it like that, it takes on a new name. We now call it hemoglobin. Anything that has oxygen bound to it takes on the term globin, like in our muscle cells. See, when the red cell delivers the oxygen to my muscles don't need it right now because I'm just sitting here. So it's going to be stored in the muscles until I do. So if somebody yells fire, I can get up and run out of here. I've got oxygen in there. When oxygen is bound to muscle cells, we call it myoglobin. When it's bound to blood cells, we call it hemoglobin. So anytime oxygen is bound to something, it takes on that term globin, hemoglobin, myoglobin, whatever type of cell it's bound to. Being bound to our red cells, hemoglobin. All right, so that's what the red cells do for us. They transport oxygen throughout the body in that way by attaching it to the heme molecules inside the red blood cell. All right, so oxygen molecules bound to the iron of the heme. Make sure you get that in your note. And thousands of heme molecules in each red cell. And that's why iron is important for us. I had one young lady in class when we were doing this part, she said, Mr. Mahone, but I'm allergic to iron. And I said, well, no. Oh, yes, I am. Yeah, my doctor told me. Well, you misunderstood what the doctor told you. We're not allergic to iron. It's essential for life. It's like being allergic to oxygen. You won't survive. Okay. So what was the young lady saying? Okay. Some people will get contact dermatitis or sensitivity in their skin to stuff called iron salt. This is the stuff that comes out of the material when it rusts. So that orange stuff, don't touch it. Your skin is sensitive to it. Now, sometimes, and that's a lesson for us because sometimes doctors, they just try to dumb things down for us because we're just not as smart as they are. We're just so dumb, we don't understand a simple concept. So they dumb it down. And what the doctor probably told the young lady was, well, just don't come into contact with any iron and you'll be fine. And the young lady walked out there believing she was allergic to iron. Okay. It's the iron salts, the stuff that comes out of the iron when it rusts, that orange stuff. That's the stuff you don't want to touch. So I think that doctors should not dumb things down because it makes people misunderstand sometimes. Okay? When you try and simplify it. Remember, when you give them a simplified explanation, they're going to pass that simplified explanation on to other people. And they're going to walk out there and tell people, I'm allergic to iron. Doctor told me don't touch any iron, so I'm allergic to iron. No, you're not. You have contact or dermatitis when you touch rust. All right. So anyway, iron is essential to human existence. All right, so oxygen molecules bond to the iron of the heme, creating hemoglobin.
I have a question, sir. This is
Yes.
Renita. Okay, the doctor also told me that I was like not allergic, but my body doesn't take iron from like food.
Okay.
So I've had blood transfusions over the years, even before all of that, because of that. So how is it actually that I'm actually making enough red blood cells if I can't get, if our blood cells is coming from red blood cells for that, we make it anyway. Never mind. It's a stupid question, just so that. Okay.
You're not. That's why we have to give you iron.
Remember, so for the blood transfusions. So
yeah. We either have to give you the blood cells themselves or we have to give you iron through a supplement.
Of course it does.
But you're going to have to get the iron. Otherwise, you're not going to be creating red cells. So, yeah, good question. If you are not getting enough iron in your body for whatever reason, you're not going to be creating enough red cells. And what do we call that when you're not creating enough red cells? Anemia. So, yeah, you're anemic. Your body's not creating enough. So we either need to transfuse you the red cells themselves, or we need to give you iron so that your body can create your red cells. Either way, we've got to get some red cells in your body. Either you make them yourself or we transfuse them to you from somebody else. So yes, that's a good question. If you are not getting iron, then you're not producing enough red cells. And we need to deal with that. So when a doctor is asking somebody's hemoglobin determination, what they want to know is what percentage of red cells in your body are actually carrying oxygen for you. If that's a low percentage, then you don't have enough oxygen trucks. You don't have enough red cells. So can anybody want to take a stab at guessing what a average hemoglobin determination should be for a person? What percentage of your red cells should be carrying oxygen for you? Requires a little bit of critical thinking. What'd you say, Chris?
I said 25%.
25? Okay. Anybody else?
About 65%, sir.
65, okay.
Like 80%?
80%, all right. Critical thinking.
100%.
100%, okay. Nobody's hit it yet.
3%.
All right. Remember that in your body, I guess I can I delete that now? That's probably there permanently. No, there we go. Right. In your body, here is your lungs, your heart, which is the pump, and then down here will represent your tissues. Let's say any organ in the body. So at any given time, half of your trucks are headed to the lungs, with the pump being to keep it going, to pick up oxygen. And the other half is headed out to drop off oxygen. So what should the basic hemoglobin determination be? About 50%. About half your truck should be carrying oxygen because the other half is returning to the warehouse to pick up more. Drop it off, pick it up. The heart keeps everything moving. Drop it off, pick it up. So you should have a hemoglobin determination of about half of your red cells should be carrying oxygen for you. The other half will be returning to the warehouse to pick up more. Percentage of red cells that are carrying oxygen for you. Okay. All right, so let's talk about this thing right here. Anemia. A decrease in the number of red cells. You don't have enough. Why don't you have enough? The most common cause of anemia is iron deficiency. You don't have enough iron. You can't make them. Think of it this way. This truck, this big white section right there, that's iron. If that section isn't there, the truck is useless because it can't carry oxygen. So you've got a bunch of trucks that don't have this tank on them. They're useless to you. So if you don't have enough red cells, the most common reason is that you don't have iron. And your red cells can't be produced because you can't make a truck without that tank on there. So if that tank's not there, the other truck, they just sit there. They're not doing anything. So we have to have iron to produce red cells. If you don't have enough red cells, that's anemia. And the most common form of anemia is iron deficient anemia. And this will be more common in women.
Yeah.
And why y'all think that is?
Menstrual cycles.
Yeah. If you have 2 million red cells in every drop of blood, how many red cells are you losing during menstruation? You're losing billions of red cells. And you have to replace all those. And if you don't have a high iron diet, you may find yourself anemic. All right. So what are the signs that somebody might be anemic? Come on, y'all.
Skin.
Y'all know.
Fatigue, bruise easily.
Yeah.
Fake nails, chipping.
They're always cold.
Okay.
Numbness.
You are tired all the time. Why are you tired? Oxygen plus glucose equals energy. If you don't have enough red cells, you don't have enough oxygen. You don't have enough oxygen, you can't burn glucose. You can't burn glucose, you're going to be tired. So you're going to be tired all the time. Same issue here, headache, oxygen to the brain. Yellowish skin. Why? Your skin isn't pink enough. You're not pumping enough oxygen into your skin. Irregular heartbeats, chest pain, cold hands all the time, decreased circulation. Dizziness going along with not enough oxygen to the brain. Leg cramps, not enough oxygen to your muscles. Insomnia, difficulty sleeping at night. All of these are signs that you might be anemic. Any type of anemia. There are
You
several.
gave me someone new about the insomnia, the not being able to sleep. I never heard that one.
Oh, poor thing, yeah. Now, iron deficient anemia, these are signs for all anemias, by the way. There are several different anemias. You see on here sickle cell anemia, megaloblastic anemia, pernicious anemia, also called B12 anemia, are all types of anemia where they're not producing enough red cells. And you see the signs and symptoms are the same for all anemias. However, iron deficient anemia has another sign. Now, a sign is something you can see. You can see somebody doing this. And what's the sign associated specifically with iron deficient anemia? Anybody know? It's something that they do. It's a craving.
They crave ice.
Ah, ice chips.
Ice. Yep.
Just sitting there chomping on them like. One point, I had this child sitting in the front of my class, y'all, and she would bring in a big cup of ice with her, sit on it, and just the whole class. Hey, get the iron in check, man. Jeez. Okay. Caught my wife doing it one day, sitting in the Burger King. I drank her soda, went back up. I thought she was going to get more soda. Yeah, she filled the thing with ice, came back. We're going to take you over and have your iron checked. We did. And her iron was so low that her red cells were pink. Iron is what makes our red cells red. Okay? And hers were pink. So she really needed iron. So what foods can you consume that are high in iron?
Spinach, meat.
Say what?
Spinach, meat, arugula,
Spinach.
kale.
Okay. Any green leafy vegetables. And I don't know if y'all remember Popeye. I'm strong to the finish because I eat me spinach. Okay. So any green leafy vegetables. What about pickles or pickle juice? Are also high in iron. And I told y'all to remember this. Where do we store iron in our bodies? Anybody?
The liver.
In our liver.
Liver. Yeah.
So other animals store iron in their liver as well. So what other food might you be craving?
Liver.
Liver and onions. That's my wife's thing, man. I just want some liver and onions. Girl, you need to get your iron in check, man, because I can't stand that stuff, y'all. I have a history with liver. My mom loved liver and onions, man. She was probably anemic all the freaking time. She loved liver and onions. So she would fix it for dinner, okay, and put that in the table in front of me. I was maybe 6 or 7, sitting at the doggone table at the big house, sitting at that freaking table, and my mom's insisting I'm going to eat that liver. And I'm insisting, no, I'm not. And we're going back and forth, man. You're going to eat? No, I'm not. Yes, you are. No, I'm not. I'm not eating that. It's nasty, dot, 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 dot. All right. By the time we got to the point where she was trying to force it in my mouth, it was cold and just, ugh. So she's got the fork and she is shoving this liver in my mouth, y'all, until I just threw up all over the damn table. And she stopped trying to force me to eat liver after that. So now, probably the one place where my wife goes when she wants liver and onions is she'll drag me off to Luby's. I just want some liver and onions. Come on, we going to Luby's. And I'll sit at a different table. I'm not lying. And they look at us like we're crazy. But no, I'm not sitting at that table with you. I'll mess around and throw up because of, my history with liver. So her and her damn liver and onions. And also just walking around the freaking house, y'all. I'm walking around, no shirt, short pants, no shoes. She's coming around, blankets wrapped around her. It's cold in here. No, get your damn iron in check. Get on my nerves, man. It's cold in here. The other day yesterday I asked her to rub my shoulder for me. Man, rub my shoulder. Her hands were so damn cold. I was like, girl, you need some iron in your blood, man. Geez, eat you some pickles or something, man. Get you a freaking iron supplement. However, if you're going to do something like an iron supplement, where you take iron pills, remember that there is such thing as iron overload disease. You can have too much iron. Makes your blood too thick and your heart overworks. So you don't want to get carried away with the iron, but you want to make sure you have plenty. My sister, man, when we were kids, when she was going through puberty and starting menstruation and all this mess, I didn't know that's why at the time, but man, when you ate the last pickle out the pickle jar, you better not pour that down the sink because she'll walk in and pick that and drink that pickle juice just straight down. Make me gag every time, like, ooh, that's just gross. Now my mama knows what's going on. She's like, boy, leave your sister alone. She needs that. I'm like, whatever, man. That's just nasty drinking pickle juice right out the jar. Going after that iron. And that's why pickles are the most common craving for pregnant women. Because remember, the baby has to produce billions of red cells. And where are they going to get the iron from to do that? From you. So the baby's taking your iron. And as a result, you need to replenish that. Another thing that's high in iron is potting soil. So don't ever be surprised if you see, especially a pregnant woman, reach into a potted plant and eat some of the dirt. They go, did you just eat dirt? And they'll probably say something like, did I? Oh, why did I do that? Your body sensed the iron in there, and it's a reflex without even thinking about it. That's why a dog eats grass when you let them out in the yard. They don't know why. It's a craving. Same reason that children drink a lot of milk. You sense that iron in there, and boom, reached in there and ate some of the dirt. Yeah. So that is what anemia is, a decrease in the number of red cells. And there are several different causes for that, but the most common is iron deficiency. That's 2 test questions right there. What is it called when a person has a decrease in the number of red cells? And what is the most common form of anemia? Iron deficiency. You see other types of anemia here: sickle cell, megaloblastic. In sickle cell, their red cells are not shaped right. Now, I want you to remember when you were a kid, you might have had, almost everybody had this toy when you were a kid. It was a ball that was down the middle. One side was usually either red or blue, and then blue or yellow or whatever, but they had shapes cut out of them. And you would pull it apart by the little handle, and the shapes were inside, and you push the blocks through the shapes. Is how many of us learned our shapes. And they had the little, that was supposed to be a star. But anyway, so the triangle block and the square block, when you get them all, you pull it apart, the blocks drop out, you do it again. Okay. Now, when red cells are not shaped correctly, when they get to the tissues to drop off their oxygen, they won't get in, they won't fit in. They're not shaped right. It'd be like trying to push the star block through the round hole. It won't go in. So that's why sickle cell, when the cells are not shaped correctly, that's why that person is not getting enough oxygen to their tissues. Okay. The other type of anemia was megaloblastic. When you produce red cells, see how that goes right through and in like it's supposed to, but they're producing their red cells way too big. They will not fit in that hole. So that's megaloblastic anemia. And a very important component of the membrane of the red cell is vitamin B12. If you're not getting enough B12, you're going to have problems creating the membranes for these cells. Either way, not dropping off, can't create them in the first place. If you don't have iron, you can't create them in the first place. So these are all forms of anemia. Megaloblastic, sickle cell, iron deficiency, you're not creating them. B12, you're not creating them. So those are the more common forms of anemia. Sickle cell, megaloblastic, and then pernicious anemia, also called B12 anemia.
So why is sickle cell anemia more common in African Americans?
It's a genetic thing. It's African American and Asian, actually. It's not just Black folks, but it's Asian people as well. And one of the misnomers out there is that it's something that happened as a result of slavery. But sickle cell anemia is just as common on the African continent as it is in the United States. So it's not just African Americans, it's African descent. Okay? So all those people in Africa right now, their people were never slaves, not to, American slavery or English or whatever. So, but they still have anemia or excuse me, sickle cell just as much as it happens in the United States. So it's not something to do with slavery. Many people believe the middle crossing, from Africa to the United States. That crossing right there was so horrible, and so many slaves died during that crossing that they think that it caused something in the DNA, and that's not how it happened. So we really don't know. It's just genetics, where we are just not producing our red cells correctly. So that is sickle cell, megaloblastic, and pernicious anemia. The most common anemia is iron deficient anemia. So we've been at it for an hour and 15 minutes. So let's go ahead and take a break. It's 9:15. Let's come back at 9:30. All right, so I am back. I see Esther's with us now. I've got you updated on the attendance, so that's taken care of. Anybody else? Jordan Carter, uh, Vanessa or Selena, Latasha? Anybody? Anybody? Okay, all right, so we'll continue. All right, so man, my left arm is really bothering me today. I got that pinched nerve up here in my back, and I can feel it all down through my hand and my fingers and all that. So if I seem a little distracted, it's because, yeah, this is distracting as hell. All right, so anyway, we have now mentioned that a decrease in the number of our red cells is called anemia, and the most common anemia is iron deficient anemia. All right. Now, before we go into this next part or section, I want to remind y'all about something. And that is that every cell on our body, or every cell in our body, excuse me, has a marker that we call a self-identifier. This is the ID badge that lets our immune system know that this cell belongs to us so that we don't attack it and destroy it. Every cell in our body has this marker except the red cells. Our red cells have markers on them, but they're not self-identifiers. And that's why we can move blood to somebody pretty easily. But moving tissue like a kidney or a liver to somebody else, we have to match those identifiers. The red cells are different. Our red cells have markers, but there's not self-identifiers. They're general markers that are common to everybody out there. And the markers that appear on our red blood cells are some of our red cells, or some people out there will have a marker on their red cell that we have identified as a marker. Some people out there on their red cells, they'll have a B marker. Now, some people out there, not as common as the others, but some people out there will have both markers, A and B. And some folks out there will have no markers on their cells. So these are the markers that appear on people's red cells, and we call them blood types. This person over here is type A. This person is type B. This person is type AB. So type A, type B, type AB. And this person down here with no marker is type O. So those are your blood types, AB, or A, B, AB, and O. All right. Now, when we want to move blood from one person to another, we have to match the markers. But that's not 100% match. And let me tell you what I mean by that. People who are type A, they have anti-B antibodies. And antibody is something that seeks out and destroys. So these antibodies seek out and destroy the B blood. So if you put B blood into an A person, their antibodies will become active and destroy all the blood you just put in them. People who have B type blood have anti-A antibodies. So you cannot put A blood into a B person. Their antibodies will seek out and destroy that A blood. So that's what we would call um, um, cross transfusing somebody. You transfuse them with the wrong blood type. All right. Now, people who have AB blood, they don't have A antibodies and they don't have B antibodies. They can't because they have both those markers on their blood cells. So AB blood, they have no antibodies. And people who are type O, since they have no markers on their blood, they have both antibodies. Both A and B.
I have both.
So this is what determines how we can put blood into another person. You see, you cannot put B blood into an A person, and you cannot put A blood into a B person. Neither one of those would work. Their antibodies would become active and destroy the blood that you just put into them. But remember that these transfusions are only based on marker, or only restricted by markers that are present on the person's blood. So can you put A blood into an AB person? Yes or no?
Yes.
Yes. Remember, they have no antibodies. Can you put B blood into an AB person?
Yes.
Yes, because they have no antibodies. Can you put A blood, can you put AB blood into an A person? Can you go this way?
No.
AB into an A person? No, because they have B antibodies. Can you put AB blood into a B person?
No.
No, because they have B antibodies. So you cannot move AB into either one of these people, but you can put A or B into this person, no problem. Okay. Now, can you put any of these bloods, A, B, or AB, can you put any of those into an O person?
Yes.
Absolutely not, because they have both antibodies. If you put A blood into this person, their A antibodies will attack it and destroy it. If you put B blood into O, their B antibodies will attack it and destroy it. If you put AB blood into an O person, both antibodies will attack and destroy it. So O cannot receive transfusions from any of these people. O can only receive blood from another O person, which is not a big deal because 44% of people on the planet are type O. So if there's somebody who's type O who needs a transfusion, there's a good chance there's another O in the room somewhere. You can expect about 44% of any group of people to be type O. So in our class right now, there are 23 people. So 44% of that would be about 11 people. So if somebody's type O, there's a good chance there's another type O in the room, since it's the most common blood type. So O's can only receive transfusions from another O. But look at it this way now. Can O blood be moved into an A person? Would that work?
Yes.
Yes. Why would that work? Because the
Yes.
O person has no markers on their blood. As a result, the anti-B antibodies have nothing to attack. They won't become active. Can you put O blood into a B person?
Yes.
Yes. No markers out here, nothing to attack. Can you put O blood into an AB person?
Yes.
Again, nothing to attack. So O can be transfused to anybody, but they can only receive from another type O person. And that's what I mean when I say it's not 100% match. There are some caveats or some rules that we can follow in here. So type O blood can be transfused to anybody, including another O. But the A's, B's, and AB's, those have to be matched. AB cannot go to an A person because the B marker would be attacked and destroyed. AB cannot go to a B person because the A marker will be attacked and destroyed. But you can put A or B into that person, no problem, because the markers will match. Okay. O can go to anybody, but can only receive from another O. All right. So now let's talk about the other part, the part that y'all have heard of before. And that is there is a third marker available. Remember, the markers were A or B. You have one of them, you have both of them, or you have neither of them. The third marker that's available, either you have it or you don't. If you have it, you are referred to being positive. And if you don't have this second marker, you are referred as being negative. Okay. Now, anybody, any one of these blood types, A positive, B positive, AB positive, or O positive, they have the additional marker. If you are negative, then you don't have the additional marker, and you can be A negative, B negative, AB negative, or O negative. Okay, now, of these blood types, which one has all three markers? Think of what the markers are. And who has all three of them? What would
Oh.
be the person? Nope, they have all three.
O positive.
Not A positive,
O positive.
not O positive. They have all three markers. So the markers are A, B, and positive. This person has all three markers on their blood, A, B positive. Now, who has none of the markers on their blood? They don't have A, they don't have B, and they don't have negative, or they don't have positive. What do we call it?
RH negative. Oh.
O negative. They have no markers on their blood. Okay, now, anybody who is, for example, A negative, there's a chance that they'll have anti-positive antibodies. So you cannot put positive blood into a negative person. Their antibodies will attack it and destroy it. However, if a person is negative, they don't have any antibodies. Remember, negative simply means you don't have the other marker. So you can put negative blood into a positive person, no problem. There's nothing to attack. As a matter of fact, this negative sign right there, that misleads people. It's thinking that you have to match this over here. Really, you don't. There's nothing to match. Negative simply means they don't have this. So if somebody's A negative, the way we should be writing that is like that. Because once you put this out here, it misleads people. Oh, there's something that needs to be matched. No, there isn't. There's nothing there. Negative means there's nothing there and nothing to be matched. So negative blood can go to a positive person, no problem. There's nothing there for their antibodies to attack. But if you put this blood into that person, you can't go this way. You cannot put positive blood into a negative person. But you can put negative blood into a positive person. So if you're A positive, and they pick up a liter of A negative, they can transfuse that to you, no problem. But they can't go the other way. Positive blood can't be put into a negative person. Now, the positive and negative, or the positive factor, known as your RH factor. Okay. If you have this, then you're RH positive. If you don't have it, you're RH negative. Now, the positive or negative, that's not the same as the rest of the body or the other markers. RH positive or negative is considered to be the body will respond like it's an allergy. If you put positive blood into a negative person, that's an allergic reaction. And it follows the same rules of all allergic reactions. Does anybody know the main number one rule for allergies? Have you ever heard it before? The number one rule for an allergy is that you cannot be allergic to something until you've been exposed to it at least once. The allergic reaction will not happen until the second exposure. So what is that telling you then? You can put positive blood into a negative person one time. The allergic reaction isn't going to happen until you do it the second time. So allergies don't happen on the first exposure. So in an emergency, if you have somebody who is A negative and they need a transfusion, and the only blood you have is A positive, you can do it one time. After that, the person will be allergic to it. So allergies don't happen until your second exposure to something. That's when you'll have the allergic reaction. The allergy starts on the first exposure, but the reaction won't happen until the second exposure. So RH factor cross transfusion is possible, but only one time. And if we ever did that to somebody, you better believe that in their medical record, it would be documented all over the record, sometimes on the cover of the record, that this person has already had a cross transfusion of the RH factor, so that nobody does it to them again. It's a risk that we take, but we only do it if it is a dire emergency. The person is going to die if we don't do this right now. Okay. So it follows the rule.
I don't mean to interrupt her, but is that a really bad thing to do to a person?
What?
Give him, if he's positive, give him negative?
No, you can put negative to a positive. That's no problem.
Yeah, but the other way.
Yeah,
Positive to negative, yeah. Is that really, really bad?
It's not something we want to do, no.
Right, right.
But in an emergency, we can. An emergency being a combat zone. People, big battle happened, people are dying around you, and this person needs a transfusion, and you don't have the correct blood type or the correct RH factor. You have the blood type, they're A, you have plenty of A on the shelf, but this person is A negative. You can put A positive in them one time. After that, it would kill them if you tried it again. So no, we don't want to get in the habit of doing that. But in an emergency, you can. Okay, so let's look at the transfusions one more time, now with both factors. This person is type A, B, AB, and O. Can A blood be transferred to a B person? No. Can B blood be transfused to an A person?
No.
No. Can AB blood be transfused to an A person? No. Remember the B. Can AB blood go to a B person? No. A blood can go to AB. B blood can go to AB. No problem. Can any of these be transfused to an O person? No, none of these can be put into this person. Can O be put into all these people? Yes, O can be transfused to anybody. Okay, now, of these three blood types, once we add the positive, who of these people can receive a transfusion from anybody? In order to be in that state, you have to have all three markers. If you have all three markers, your body won't reject anything. So what blood type can receive blood from anybody?
O negative.
A,
Oh.
B, positive. That person is known as the universal recipient. They can receive blood from anybody. So when we check your blood type and find you're AB positive, give me any blood we got. They can receive from anybody. So if we've got B positive on the shelf, yeah, go and give me that. We got A negative on the shelf, yeah, go on and give me that. They can receive a transfusion of any blood type. Now, what blood type can donate to anybody? It has to be somebody who has no markers on their blood whatsoever.
Oh.
And who is that person?
Oh,
Oh, what?
Oh.
Oh, what?
Oh. Oh.
Oh,
Oh. Nothing.
oh, nothing, right? What do we call that? Oh, negative. That person is your universal donor. Their blood has no markers on it. So what does their blood look like? It looks like that. There's no A on there. There's no B on there. There's no positive on there. They have nothing on their blood cells. That blood can be given to anybody because we only reject blood based on these markers, A, B, or positive. They have none of them. Their blood can be put into anybody. So this is the blood that we want during emergencies. Explosion. Did y'all see the explosion that happened in Beirut yesterday?
In Lebanon.
Yeah, man, that thing was boom. It looked like shit. And they caught it on several different cameras from several different angles. Y'all, that was a horrible explosion.
did you hear their excuse?
Huh?
Their excuse?
The
What was it?
fertilizer.
They were blaming it on some security issue, something like that, on their where they house their explosives.
Uh-huh.
That's crazy.
Yeah, there was supposedly some stuff that they had all put into a warehouse because they found it on the something like that. So they stuck it all into a warehouse and something ignited it. But you know what? Fertilizer is also used to make bombs.
Yeah, it was the fertilizer, the ammonium.
Yeah, so they may just be saying that, but it's also that's what blew up the building in Oklahoma City, the Alpha Chimera building. Was just fertilizers. So anyway, a fertilizer bomb. So anyway, that stuff is used to make bombs. So why in the hell would they put it stored all in one warehouse? But anyway, a situation like that, 3,000 people injured. How much blood? Did y'all see the clips? Them people walk around blood. The one lady, guys, it looked like she just jumped in a bucket of blood. She was covered head to toe. From little, I guess they're all just little cuts because she was up and walking. So I guess they're all just, debris that hit her in all these different areas and she was bleeding everywhere. So in that scenario, what blood do we want to have a lot of on hand?
Be positive.
Oh, negative. The stuff that can be given to anybody. This is what we want to have plenty of. O negative blood. When you come into the ER or wherever, the first thing that we're going to have to do is check your blood type. Once we have your blood type, then we have to call the blood bank and order a match for you, unless we have O negative blood on hand, in which case we don't even have to check your blood type because O negative can be given to anybody. So in an emergency, this is the stuff we want. It's going to eliminate 2 steps. The first step, finding out what your blood type is. The second step, ordering blood that matches you and waiting on it to come up from the lab. If we've got O negative in the refrigerator, shit, give me a liter O negative. Doc says, hey, hang a liter O negative, because it can be transfused to anybody. Don't ever, don't ever go to the blood bank and donate blood and let them find out that you're O negative. Shit. They'll be blowing your phone up, man. Sending you out those little robocalls, you know, yeah, we need some blood. Come on down and donate. You're O negative. We want your blood. They find out you're O negative. You go into a special database at the blood bank. And when they need blood, they just kind of hit a button and robocall everybody on the list who's O negative. Come on down and donate some blood. So you're going to be getting calls all the time if they find out you're O negative. So don't do that. They're going to be, it'll be like ridiculous, y'all. Every 3 or 4 days, come down and donate. Come down and donate. Because you're O negative. We need that blood. O negative is a universal donor. And in your PowerPoints, I'm almost positive that that's red. There it is. O negative is a universal donor. AB positive is a universal recipient. Have that in your notes. And if it's not deep enough for you yet, it's going to get deep. We're getting to the deep end of the pool on this one. I'm going to throw something else in there. Okay, so this is everything we've been talking about. Type A, type B, AB, and type O. They have both anti-A and B antibodies. Those are your blood types. If we give you the wrong blood type, if we put A blood in a B person, that's going to cause a hemolytic reaction. Hemo is blood, lysis, to break down or destroy. So all that blood we put in you, your spleen is going to break it down and destroy it. The antibodies are going to become active. We're going to be pulling all of those blood cells into your spleen. Remember, spleen is where blood cells are destroyed. So all those red cells are going to be pulled into your spleen to be destroyed at one time. If we put a liter of blood in you, that's the wrong blood type, that's a liter of blood, a bag of blood that gets sucked into your spleen to all be destroyed at one time. What's going to happen to your spleen? It's going to swell up real big. And if it swells too much, it's going to rupture. Splenomegaly, splenoragia. Enlarge and then rupture. And all that blood into your spleen is going to gush out into your body. And that's probably going to kill you. Once the spleen ruptures, you bleed to death inside. That's how dangerous it is to give the wrong blood to somebody. And that's why transfusing blood is no joke. Now, medical assistants probably won't get involved in that very much because we don't transfuse a lot of blood in clinics. But PCTs, where y'all at?
Okay.
Yeah, on them wards, that's where we transfuse blood. And y'all will get involved into this part. Now, what does that mean? You walk on the ward for a night shift. Oh yeah, Mahone's here, ready to work. Oh, by the way, Airman Mahone, we're going to be doing a blood transfusion tonight. Damn. Shit. What does that mean? That means that you're going to be sitting in the room with that patient. Period. Nobody's ever alone when receiving a blood transfusion. So they'll come in, they'll hang the blood, And you will take their vital signs every 5 minutes for the first 15 minutes of that transfusion. Every 5 minutes. So you might as well just not take the blood pressure cuff off. Put it on their arm and leave it. Every 5 minutes, blood pressure, pulse, blood pressure, pulse, blood pressure, pulse. And after the first 15 minutes, it's blood pressure, or take their vital signs every 15 minutes after that until the transfusion is done. So you're not going to leave the room that night as long as that person's on blood. And the doctor walks up, comes back up, checks everything and said, yeah, let's go on and give him another liter. Damn. That's another hour to 2 hours of sitting in a room with that patient. You cannot leave. Okay. So it makes for a long night when you're transfusing blood, especially to more than one person on a ward. So PCTs, get ready for that. The blood transfusion vital signs. Every 5 minutes for the first 15 minutes, and then every 15 minutes after that until the transfusion is complete. You do not leave anybody alone in a room while receiving blood for the risk or danger of hemolytic reaction. So what do we do to prepare to transfuse somebody? Okay. We get in their medical record and we send their blood type down to the lab. The lab sends up the blood that we need to transfuse to them. Once we receive the blood on the ward, you and I will stand there together and we'll go through the patient's record and the blood that they just sent up. And we'll compare and make sure that all the patient number, we use patient numbers today, back in the day we used social security numbers, make sure that they match, that the blood type is correct, ... And I read it out. Mr. John Jones, patient number 14675. Patient number 14675. This is the other person reading it back to me. Type A positive blood. Type A positive blood. Okay. And then we switch and we do the same thing again. You read it out and I confirm it. So that has to be done twice. And now we're ready to go down and transfuse the patient. So this is a big deal, y'all. We don't just go slamming blood into people. A hemolytic reaction can happen in the first 15 minutes of the transfusion and could kill the person. Okay. So cross transfusions, we really need to be on top of this process, making sure that we're not cross transfusing somebody. It can kill them. The RH factor we mentioned, you either have it or you don't. If you have it, you are positive. If you don't, you are negative. And then the where do I want to go next? We'll go here. This is where it might get a little deep. Okay, now, blood types between the mother and the baby usually is not an issue. The mother's type A, the baby's type B. It's not going to be a problem, unless there's a problem with the placenta. In other words, it's an abnormal condition. Other than that, the mother's blood type does not have to match the baby. However, the RH factor can be an issue. So you've got mom and you've got baby. First of all, let's talk about what we used to do to determine whether this was your baby, Chris, or Isaac, or Jaime. Is this your baby? We know it's her baby, but is it yours? Okay. First of all, we're going to look at the baby's blood type. Baby is type B. All right, now let me tell you this before you front yourself in class. You will be the blood type of one of your parents. That's a gimme right there. You will be the blood type of one of your parents. Now, what I mean by front yourself in class, because I have had students say, Mr. Mahone, that's not true. Really? And I know what they're getting ready to say. Because my mama type A and my daddy's type B and I'm type O. So I don't match either one of my parents. Then you need to go home and have a conversation with your mama. Because your daddy is not your daddy. Sorry. So don't front yourself in class, keep it quiet, and then just go home and talk to your mama. Mama, now how come? Right. Now, that reminds me of this old song. This song has been recorded in reggae, country and western, and soul. I guess it's just a cool song. And I don't know the name of it, but I've heard the reggae version and the country and western version of this song. Okay. In the song, the boy meets a girl that he falls in love with, and he wants to marry this girl. And he goes to his dad. He said, Dad, I love this girl and I want to marry her. And the dad says, you can't marry that girl because that girl is your sister. But shh, mama don't know. Okay. Anyway, so you can't marry that girl because daddy been out there, and got another baby, and that girl is your sister, but shh, don't tell your mama. Okay, so that's the first verse of the song. Don't tell your mama. Okay, so the second, the guy goes to his mama, and he says, Mama, I love this girl, but daddy says I can't marry her because the girl is my sister. And the mama says, boy, go ahead and marry that girl because your daddy's not your daddy, but shh, he don't know. So the second verse is daddy don't know. So the first verse, mama don't know. Second verse, daddy don't know. I had to play it back and go like, wait a minute, what did they just say? So anyway, you will be the blood type of one of your parents. So how did they do this back in the day? All right. So you have a baby that's type B. So they're first going to go and check mom. Now, unfortunately, if mom is type B, the daddy could be anybody. Sorry. Baby matches a mama. But let's say mama is type O. What's the dad's blood type? The father of this baby must be
B.
type B because the baby will match one of the parents. But still, unfortunately, it's any B person out there could be the daddy of this baby. So what do? They get the names from mama. They test those men, and whoever's type B is the father. But what if there are two men out there that this woman has slept with, and they're both type B? Either one of them could be the daddy. So the blood typing didn't confirm that you were the father of this child, but it could eliminate you. So for example, you say, well, I slept with this guy over here, and this guy is type A. Nah, sorry, not the daddy. It's somebody out there who's type B. And that's the closest they could get. So what would they do in this case? Baby's B, mama slept with two men, they're both type B. What would they do on the birth certificate? Whatever mama said. Now, how accurate was that shit? Whatever mama said. And so, and you didn't have to, they didn't ask you, they didn't ask the male, so we're going to be putting your name on the birth. No, they asked the mother, and the man got nothing to say about it. So whichever name she wants on the birth certificate is the name they'll put on there. Now check this out. This dude right here, he's in the military. This dude over here is unemployed, living with his mama. Guess what name's going to be put on the birth certificate? Them right there. Get them military benefits and da. Yeah, go and put him on there. They best suited, whatever. So this was nowhere near accurate, y'all. And people were getting caught up in shit back here, whatever name the mama put on there. And I got caught up in this. I sure did. I was in the Air Force for about 10 years. Yeah, it was just about 10 years. When I got a letter from some law office in St. Louis telling me that this 10-year-old girl is my baby and I haven't been paying child support and da 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 da. And y'all, that is a big deal in the military. There wasn't no deadbeat dads in the damn military. And when I went to see the lawyer on base, and these people, you know, these are lawyers that work for the Air Force, and this guy's looking at me and he says, if this turns out to be your child, you better have a way to prove that you didn't know the child was existed. Otherwise, you could go to jail. And I'm like, I never heard of this kid. I knew the lady, yeah. I knew the lady, yeah. But I never heard that she was pregnant or about any kid or anything like that. And he said, you need to be able to prove that. Otherwise, you're going down as a deadbeat dad. I'm like, oh, shit. But good news for me. See, what had happened was, y'all may be old enough to remember this. None of y'all are from Missouri, but at one point, the state of Missouri said, no more of this welfare crap. If you have a baby and that baby obviously has a daddy, we need to find that daddy or we're just going to cut off your child support, your welfare. You need to give us a name or we're going to cut off the welfare. And so the girl gave them my name. And they, But anyway, so now the good news is that right at that time, there was this new science emerging. This was in I joined in 82. This was 1992. There was this new science emerging. DNA. Hey. And so the lawyer said, here's what we're going to do. He sent them a letter to that same, to that law office. He sent them a letter telling them with what they call a voucher to take the baby to the closest military base and they will do a DNA test on the baby. And they DNA tested me. I was in Greece at the time. They DNA tested me over there. And we'll see if the DNA matches. All right. They sent that letter to the legal firm and didn't get a response. A month went by. And I'm at the lawyer saying, heard it? No, we still haven't heard anything. He said, I'm going to send the letter again. So he sent it again to the same law firm. This time, about, I don't know, a week and a half, 2 weeks later, he gets a letter from that law firm saying, who are you? We ain't never heard of this Robert Mahone. What are you talking about? So he started a dialogue back and forth with the law firm, saying, now the girl's name was Denise Williams. And he said, you never heard of Denise Williams? You don't represent Denise Williams? He said, no, we never heard that name before. But we have a Lovey Williams who works here as a paralegal. That heifer's sister took the letterhead from that legal firm and sent it to me as if, you need to start paying blah, 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 blah a month. So she misrepresented the legal firm that she worked for. Now, guys, if you want to piss off somebody, the people you probably don't want to piss off is a freaking lawyer. The people who know how to sue your ass. And so she misrepresented their legal firm, and they took all kinds of action against her. And but the Air Force still didn't let me off the hook. They still said, yeah, well, this case is still open with us, regardless of how it was initiated. We're still wondering now, are you a deadbeat dad? And fortunately for me, well, unfortunately for me, Denise, she never took the baby over to the Air Force Base, which was only about 20 miles from where I live. She never took them over, and they never did the DNA testing. So after 3 months, the Air Force just dropped it. Obviously, you know, if you were, she would have done everything, because you know what kind of benefits are going to come your way if you show that this child is the child of an active duty military person, you can get all types of benefits. And who wouldn't want that? For a 20-minute drive over to the Air Force Base to prove it. She never went over there. So anyway, I was caught up in that a little bit, trying to prove that I was somebody's . That was back in the day again, where whatever name you put there, or whatever name the mother said, is what went on the birth certificate. So anyway, so you will be the blood type of one of your parents. And you know that blood typing, to do that, is just not accurate at all. It was just the only way they had at the time. Today, we're going to do DNA testing. And DNA testing will show that a certain number of markers on the baby's DNA will match both. Half of them will match the mother, the other half will match the father. So you take the baby and you first match up their markers to the mother's. And whatever doesn't match mama, you'll find in the daddy's DNA. So all those that don't match will line up with dad's. So that's how they determine the mother and the father, the baby being a combination of both of them. Okay. So that is what they do today. Now, as far as the RH factor, if mama is type A and baby is type B, that's not going to be an issue, because the blood types will never cross over the placenta unless there's a problem with the placenta. Now, here's what will be a problem. If mama is RH negative, but the baby is RH positive, this proposes a problem, because people who are negative have anti-positive antibodies. And those antibodies can cross the placenta and attack and destroy the baby's blood. It's what they call RH incompatibility. Between the mother and the fetus. RH incompatibility. Mother's negative, baby's positive. That's the only time it's going to happen. If it happens the other way, mama's positive, baby's negative, no problem. But if mama's negative and baby is positive, that can be a problem. Blood types don't matter. Whether they're both A, both B, A, B, O, none of that matters. But if mama's negative and baby's positive, you might end up with an RH incompatibility.
Hey, sir, is that like where the baby is deformed or handicapped?
No, the baby won't be born.
Oh, okay.
They'll be destroyed. The mother will have a miscarriage.
Oh, okay.
Long before the baby has a chance to be born. Okay. Now, unfortunately, we don't know if the baby's going to develop positive blood or not. And by the time we realize it, it's too late. So, any mother who is negative, as soon as we find that out, we're going to assume that this could happen to you. Anybody negative blood? Got a baby, had negative blood?
I got negative.
But you had no baby though. Anybody had a baby, it's got negative blood, got pregnant with negative blood? All right. If you do, the doctor will immediately give you a shot of Rogam. And that will prevent the mother from producing these antibodies. You see this RH incompatibility between the mother and the fetus, that's in allergy, believe it or not. And do you remember the rule for allergies? You can't be allergic until you've been exposed at least once. So this will not happen on the first pregnancy. Only the next one. So the RhoGAM shot is not to protect this baby, it's to protect the next one. On this first exposure right here, this is where the mother will produce the anti-positive antibodies, just on the first exposure. And RhoGAM prevents you from creating those. So the RhoGAM shot is not to protect this baby. This baby will be born no problem, as long as it's the first. The second one is what's going to be the problem. And the next time you get pregnant, as long as you have these RhoGAM injections right here, some doctors do one, some doctors do two during the pregnancy. As long as you have those, then the next time you get pregnant will be like your first time again. And what do we do there? RhoGAM again. And we keep going to protect the next baby down the road. Not this one. Protect the next baby and so on. So every time you get pregnant, you're going to have those RhoGAM injections. And your body will never produce these antibodies. So that is what happens when mama has negative blood and the baby has positive blood. Remember, it's going to be an allergic reaction. So if you know somebody out there who only goes to the doctor to have their babies delivered, for example, they get pregnant, they don't do like prenatal care, they just go down to the hospital when it's time to deliver. Okay. And you find that they have one baby, no problem, and then a series of miscarriages afterwards. That might be what happened. They didn't get the RhoGAM injection here. And therefore, they developed the antibodies that attacked every time they got pregnant again. And then, after several miscarriages, they have baby number 2. What happened? This baby right here did not develop positive blood. This baby was born A negative. Remember, every time they get a positive, it's going to miscarry. So several, and then boom, they finally developed one baby with negative blood. They had that baby, no problem. So they might say, yeah, there's so many years between my kids because I had several miscarriages. RH incompatibility, more likely. But like I say, that's when it's going to happen, when somebody who is not, when is that open? Close that. Damn it. Anyway, somebody who is not seeing the doctors when they get pregnant. All right. So that is, let me go on and put the slide up. I don't even, there it is. Erythroblastosis fetalis. Erythro is red. Blasto is to produce, not to destroy, but to create. Erythroblastosis fetalis. The baby is creating red cells with a RH incompatibility. Erythroblastosis fetalis. RH incompatibility between the mother and the fetus. It's an allergic reaction. So see right here, first pregnancy, okay, but mother gets exposed to the RH factor and makes antibodies. So after that, it'll always be miscarries. And that's why any lady who gets pregnant, who has negative blood, the doctor's going to go on and do RhoGAM shots to protect the next baby down the road. Erythroblastosis fetalis. RH incompatibility between the mother and the fetus. Now, sometimes there are blood group incompatibilities. For example, mother's type B, baby's type A, but it usually doesn't happen. It can happen, but it usually doesn't. It's very rare. And they'll usually find out that there's a problem with the placenta. And the baby's blood and the mother's blood are actually mixing. And that should not happen. When you have a baby in the womb, oh, damn it, that's going to be there from now on, probably. I don't want to add a damn note. Close it. Anyway, now it's going to be distracting me. What was I talking about? Damn, see, that's your ADHD. I came back here to draw something. I don't even remember what it was now. All right. So anyway, I know what I was going to do. The mama, the umbilical cord, the placenta, the baby. Mother's blood comes up to the placenta, drops off its nutrients, and returns. Baby's blood does the same thing. Comes up to the placenta, picks up the nutrients, and returns. So the mother's blood and the baby's blood never mix in the womb. If there's a problem with the placenta, that might be happening, where mama's blood is getting into the baby. That's the only time you'll have a problem with mama's type A and baby's type B. If mama's blood gets into the baby or baby's blood gets into the mama, there's a problem with the placenta. It's not doing what it's supposed to do. So the bloods don't mix in the womb. And I'm going to fix this by turn it off, turn it back on. Yeah. Remember, if all else fails, turn it off, turn it back on. Shit. Anyway. Oh, look, it didn't fix the problem. Damn it. I go here and I can't delete these boxes now. Here we go. Really? I just created another one. Oh, come on. I'm on my nerves now. All right, so anyway, that's erythroblastosis fetalis. Okay, and have this in your notes. O negative is a universal donor. AB positive is a universal recipient. I know y'all not seeing a lot of questions in here, but remember that the blood and the heart will be tested on together. A lot of heart questions in this one. Okay. A few blood questions, as you can see, but most of the questions will be over the heart, which will be covered tomorrow. All right, so that's the universal donor and universal recipient. And that brings us to the end of the red cells. So let's do a quick review. Just with the red cells. Most numerous cells produced in the bone marrow, approximately 2 million per second. Now, what's not on this slide is that each blood drop contains about 2 million red cells. So to say that your body produces 1 drop of blood per second is not a stretch, but this is just that one drop contains about 2 million cells. They have no nucleus, so they cannot reproduce. As a matter of fact, the red cells are one of the few cells in our body that don't have a nucleus. And the only other ones I can think of are the skin cells. There are some skin cells that don't have nucleus either. But because of that, they can't reproduce. They live for approximately 120 days. Old red blood cells are destroyed in the spleen. I'm almost sure that is a test question. Old red cells are destroyed in the spleen. Just go ahead and get that in your notes. We save this, and I'll send an updated version of this when we get done today. Old red cells are destroyed in the spleen. And there's another one. Where is it? Let me just go on and do it. No, I didn't want to do it that way. Let's do it this way. Oh, I wanted to copy this one. Let's delete this one. And this is the one I want to copy. All right. And I want to say in here that. After a red cell is destroyed, The heme and iron are stored in the liver. And again, I'll send out an update of this when we finish. After a red cell is destroyed, the heme and iron are stored in the liver. Oxygen molecules bind to the iron of the heme. Hence the term hemoglobin, the percentage of red cells that are carrying oxygen in your body, the hemoglobin determination. The two questions about anemia: decrease in the number of red cells, and the most common anemia is iron deficient. And then no other questions until we get down to O negative and AB positive. And that brings us to the second of our formed elements, our leukocytes. Now, leukocytes are white cells. They provide immunity for us. They are the immune system. They seek out and destroy those things in our body that do not have a self-identifier, including your own cells if they become unrecognizable. Remember that. Oh, really? Okay. Away again. Okay. That self-identifier we talked about that says, I belong to this body. If that thing becomes damaged and unrecognizable, then your white cells will attack this as well, as if it didn't belong here. And what do we call that? Autoimmune. Your immune system is attacking your own cells because the marker is not recognizable. Okay. So anything in your body that's not recognized by your immune system will be attacked and destroyed. Think of it like we said, like the ID badge you wear at work. And what happens if you put a bunch of stickers and pins on your ID badge because you don't like the picture? Technically at work, what should they do? If I look at that badge and I can't see Quest College on there with your picture, I'm supposed to kick you off campus. Doesn't that do any damn good to have an ID badge that somebody else can't read? Have you ever been to a clinic or something or a hospital and you couldn't read the ID badge of the person who was caring for you? Did you say something? I'm nurse so-and-so. Well, you might be. How do I know that with your badge all turned around like that? You could be anybody. And yeah, they're going to get a little bit of attitude, but I don't care. You could be any freaking body walking in here putting your hands on me, saying that you're so-and-so. Turn the badge around to where I can see it. At the VA hospital, they are serious about that shit, y'all. Everybody, ID badge must be visible, and they have the big RN, LVN, PCT, doctor to let, or MD to let people know who is walking in their room putting their hands on you. And one day I'm at the VA hospital, and I was in scrubs that day, and I'm going up for my cardiology appointment. I'm standing on the elevator. And this lady gets on the elevator and she stands for a second and she's glancing over at me. And finally she says, "Where's your ID badge?" I said, "It's in the car." "Well, you shouldn't be in the building without your ID badge on, and and you people, blah, 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 blah." And I let her get her little port said, and I finally said, "I don't work here." Oh, you don't work here? No, I don't work here. When she asked where my ID badge was, it's my Quest College ID badge. It's in my car. Where's your ID badge? It's in my car. Well, you people have got to wear your ID badge. That's the law or the rule here. You're breaking the rules. Lady, I don't work here. Oh, well, yeah, you just made a fool out of yourself. Just shut up because you're just going to make it worse. You're going to chew me out because I don't have my ID badge. I don't even work at the freaking place. So when her first questions out of her mouth, which should have been, do you work here? And I'm sure that's what she'll say next time. Excuse me, do you work here? Yes, I do. Where's your ID badge? Anyway, but the VA is big about that, y'all, being able to see your ID badge and who you are. So that's what a self-antigen is, okay? Our immune system will attack anything that doesn't have the ID badge that says, I belong to this body, including your own cells if it's not recognized. All right. So there are 5 types of white cells responsible for finding these things and destroying them, anything that gets inside us. And they are typically specialized. They go after the thing that they're designed to go after. For example, the most numerous of our white cells are called neutrophils. And they attack and destroy. A little bit thicker. All right. Still not thick enough. I want thicker. I want thick, 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 thick. All right. Neutrophils, most numerous of our white cells, and their job is to destroy bacteria. We have more of these than any others because we've always got some bacteria in our body. To find a body without bacteria that's impossible. You'd be like you ever heard of the bubble boy? The people who live inside bubbles, even they will have some bacteria in their bodies. So since we have so much bacteria in us, we have more neutrophils than any other of our immune cells. They specifically find and destroy bacteria in us. And this is where we start looking at the CBC, the complete, doggone it, the complete blood count, CBC. Mahal is going to get a CBC. All right, Doc. What do they want to know? They want us to send a lab sample down to the lab, or blood sample to the lab, and the laboratory people will go in there and they will see the number of cells that you have of any particular type. For example, with your neutrophils, or which one are we got? With your neutrophils, over years, and just doing different people over generations and years of doing this, they found that the average neutrophil count in a person would be something like 1,200 to 1,500 per millimeter cubed. So they're actually going to go in and count your neutrophils. And if you fall anywhere outside this range, that's something reportable to the physician. For example, your neutrophil count is 2,500. That's way above normal, which means what's happening in your body is fighting off a bacteria, because that's what neutrophils are responsible for. So that's why the doctor wants a CBC, to try and figure out what's going on in your body. If your neutrophil count is elevated, it's a bacteria. And I never got into memorizing the actual cell counts and what the average is in people. So I don't know that neutrophil, the average count should be 1,200 to 1,500. I don't know that because I never got into memorizing them. Why not? Well, no, why wouldn't you memorize that? Because by law, whenever you send down a lab sample to the lab for a cell count, it's going to come back just like this. Yeah, on the lab slip or on the computer screen, when they send the results, it's going to show you the normal range. And if your patient's count is outside that normal range, it has to be produced or printed in a contrasting color. So that's exactly how well, actually, let me do it the way it will appear on the lab slip. It'll show you the normal range, 1,200 to 1,500. And then it'll give you the patient count. If the patient count is outside that range, it must be printed in a contrasting color like that. That's why I never got into memorizing them. They'll always be on the lab slips. That's the law. It has to be that way. It calls the doctors and people's attention to abnormal cell counts. It's got to be printed that way. Show you the normal range and then your patient's range. If the patient is outside the normal range, it'll be printed in red, typically. So it's letting us know that this patient is having a bacterial infection. The doctor will treat them with antibiotics and send them home. So that's what we do cell counts for, because each one of the white cells is responsible for a different thing. In this case, bacteria. All right. The next white cell is called an eosinophil, and its job is to destroy allergens and parasites. The things that you get into that you're allergic to, and the parasites that you get in your body. Hookworms, tapeworms, pinworms, and so on. Parasites. That was a Jeopardy question yesterday, by the way. I can't remember the exact question, but it was a parasite. It's the Greek name for the thing that gets inside your body. It was the Greek word for, it was something. The Greek word for ... and the answer was parasite. Oh, I know what it was. The Greek word for somebody who eats at your house but doesn't pay you, or something like that. But anyway, and the word was parasite. So eosinophils will destroy allergens and parasites. So you've got bacteria, allergens, parasites, all being destroyed by these cells. All right. The third type of white cell is called a basophil. Now, these don't really destroy anything. But you see what they do? These are what causes symptoms that you have when you're having an allergic reaction. And those symptoms are caused by the release of these two substances, histamine and heparin, the two H's. Histamine you've heard of before. That's the stuff that causes the itchy, watery eyes, the runny nose, and then the swelling at the site of the infection is caused by heparin. So histamine is itching, watery eyes, and any swelling you're having during an allergic reaction is caused by heparin. Histamine and heparin. So they're responsible for the symptoms of allergies. They don't fight off anything. They just release these two substances when you get an allergy in your body. Not only allergies, but also damage to the skin. And that's why if you get a good cut in the skin, while that cut is healing, eventually for a little bit, it's going to start to itch. The basophils in that area releasing histamine. Did anybody do what we did as kids at school when you take a piece of fiberglass to school? Did anybody ever do that and rub it on the other kids and it made them itch? And we didn't know at the time, we didn't know why it made them itch. But what is the stuff we're rubbing on them? It's called fiberglass. When you rub it on them, it causes minute cuts in their skin. Not enough to bleed, but enough to activate the basophils in that area. And the basophils start releasing histamine. Oh man, you got me. Yeah, I got you. Those basophils doing that to you. That's also, now did y'all know that when you get a mosquito bite, the mosquito doesn't put anything into you? It only takes out blood. Then why does the thing itch and swell up? Histamine and heparin. Even the tiny mosquito bite is enough to activate the basophils in that area. So mosquito bites itch because your basophils release histamine right there. And they swell up because the basophils release heparin right there. So that's why the mosquito bite does what it does, activating the basophils in that area. All right. So we had neutrophils for bacterias, eosinophils for allergens and parasites, basophils for the response of the symptoms of allergies, and the fourth type of white cell is called a monocyte. And you can see here that monocytes are generic. They fight whoever needs help. So if the basophils are being, or if your neutrophils are being overrun by bacteria, they call in the reinforcements. The monocytes show up and join the battle. Now, unfortunately, a high monocyte count can be an issue because they take a long time to reproduce. And it means that your body has been under attack by whatever for quite a while. So if it is a bacteria and your basophils or your neutrophils are losing the battle, these things get called in to help with that bacteria. But it takes a long time for them to reproduce. So what that means is that you've had this bacteria in your body for a while. So when we see a high monocyte count, we're going to start looking for infections that people typically have for a long time, like STDs or cancers. I know cancer is not a bacteria, but our body attacks those cells as if they are. So if you've got a cancer or an STD, like gonorrhea, syphilis, something like that, you all will typically see an increased monocyte count. So they're the backup or the reinforcement, takes a long time to reproduce, and an increased monocyte count is usually not a good sign. There's something been going on in your body for a while now. All right, so those are the first 5 types of white cells and what they're responsible for. The ones in red, know them. In other words, which of the following types of white cells is responsible for destroying bacteria? Which of the following types of white cells is responsible for destroying allergies or parasites? Which type of white cell is responsible for the symptoms of allergies? So those are your first 4: neutrophil, eosinophil, basophil, and monocyte. When we come back from break, we'll talk about the 5th type of white cell. And again, we're getting into the deep end of the pool again. So let's go ahead and take a break. It's 10 till. Come back at 5 minutes after. Give us a 15-minute break. All right, so we're back. And we said that there are 5 types of white cells. We've talked about 4 of them. The 5th type is going to take us into the deep end a little bit. The 5th type of white cell is called a lymphocyte. And there are 5 types of lymphocytes. Okay. And let's go through each one of those. What do lymphocytes do? They attack and destroy viruses. The one thing we haven't talked about. The neutrophils for bacterias, the eosinophils for allergens and parasites, and the lymphocytes destroy viruses. Now there are, it shouldn't read that way. I need to change this. There are 2 types of lymphocytes. The first one is called a T lymphocyte. And there are 5 types of T lymphocytes. Okay. First of all, well, let's do it this way. Let's go into here. All right. Let's first talk a little bit about how viruses work and why we need 5 types of lymphocytes. Here comes my wife. She's been driving my car all week, getting on my nerves, man. She don't want to drive her little funky car, even though it's a brand new. We just bought the thing last Wednesday, so it's only a week old, but she don't want to drive it. So she drives my car every freaking morning. So here she comes. She's wearing a dress today, looking all cute. It was good look. Yeah, there go my baby. Look at her. Yeah, looking how cute in her little dress. Anyway, the 5 types of how do viruses work? Yeah, got me all distracted now. How do viruses work? Okay, first of all, a virus cannot reproduce on its own. It can only do that inside a living cell. So the attack on viruses has to be multiphasic. The T lymphocyte will destroy the virus itself, but we also need to destroy any cell that the virus gets inside. So some of our lymphocytes or some of our T cells are designed to destroy just the virus. Others are designed to destroy infected cells. So that's why we have to have this multiphasic attack on viruses. Not just the virus, but any cell that the virus has infected. In the classroom, I usually do it this way. If we are all students in a classroom with your teacher, anybody who comes into our classroom that doesn't belong there, that person is an invader. They're a virus. They have to be destroyed. And any students that they interacted with will also have to be destroyed. All right. So that multi-focused attack on viruses. All right. So what cells will be doing that? First of all, we have a cell called a macrophage. Macro means big, phago means to eat. So these are big eaters. That's the first line of defense. They go after the virus itself. Okay. And so do the natural killers. Anything that shouldn't be here, they both will attack the macrophages and natural killers. The helper T cell is the teacher in the classroom. All right, so how does this happen? A virus gets into your classroom. The first thing that has to happen is the helper T cell has to identify that there's a virus in here. That's the first step. And that might not happen for a couple days. In a classroom, think of it this way. The instructor standing up there teaching, somebody opens the door, the teacher might not see them right away. They might just keep on teaching. But all the students might see them, but the teacher doesn't. The immune system isn't going to do anything until the teacher or the helper T cell turns around and says, hey, what are you doing in here? Boom, we activate the immune system. So the helper T cell is in charge. It activates the immune response. Once the teacher identifies this thing as being here, hey, you shouldn't be here, I'm going to send over macrophages and natural killers, and they will destroy the virus. Scenario ended, right? Virus is dead. No, we still have these cells, these students that have been infected. So now we're going to send over another cell who's going to go after all the infected cells and destroy those for us. That's called a cyto, meaning cell, toxic, meaning poison, cytotoxic T cell. His job is to destroy infected cells and get these destroyed. Now the scenario is handled. We've destroyed the virus. We've destroyed the infected cells. Different cells responsible for each. So for the virus, we're going to use our NK cells, our natural killers, and our macrophages, our big eaters. And they will take out the virus. The cytotoxic T cells will then go and destroy any cells that were infected by that virus. Now the scenario is handled. Okay, so let's look at the list again. You get a virus in your body. The helper T cell will recognize that virus. It will send macrophages and natural killers over to destroy the virus itself. Then it'll send the cytotoxic T cells over to destroy the infected cells. But we're still not finished yet, because we don't want that thing to come back in us again, causing problems. So I'm going to create a memory T cell that will recognize the infection if it ever comes in again. So let's look at the scenario of the classroom again. You have a classroom full of students with the teacher up front. The virus comes in. We send over natural killers and macrophages to destroy the virus itself. All those cells that got infected, we send the cytotoxic T cell over to destroy those. So now we're virus free. However, we don't want to get this same virus again. So I'm going to assign a memory T cell so that that virus ever comes in again, boom, take that bad boy out before it gets a chance to infect anything. The immune system will respond so quickly that none of our other cells will get infected. So we create a memory cell to remember previous infections. And lastly now, the virus is destroyed. The infected cells are destroyed and replaced. So now we have a memory cell in case we ever get that infection again. And then this person over here, the suppressor T cell, turns everything off, sends everybody back to work. Okay, guys, let's get back to learning. Everything is okay now. So those how our T cells work together. to keep infections at bay and also keep you from getting the same infection again. And let me rephrase that. It doesn't mean you won't get it again, but when you do, your immune cell will respond so quickly that it doesn't get a chance to make you sick by infecting other cells. Okay, so that's our T cells. The helper T cell, the macrophages and natural killers, the memory T cell, the cytotoxic T cell. Hey, baby. Excuse me, y'all. I'll be right back. All right, so our cytotoxic T cell that destroyed all the infected cells, memory T cell to remember the infection if we ever get it again, and then the suppressor T cell to turn off the immune system and send everything back to normal. And that's them listed right here. All right. So that's how we fight off viruses. Helper T cell activates the macrophages and natural killers to destroy the virus itself, activates the cytotoxic cells to destroy the infected cells, the memory cell to remember the infection, and then the suppressor T cell to turn everything off and go back to normal again. Now, how do we use this to our benefit? Or how can we manipulate this system a little bit? Let's say that I hear that there's a virus going around infecting people. What if I can bring you in and introduce just a little bit of that virus to your body, stimulating your body, not enough to make you sick, but enough to stimulate the production of a memory T cell? What have I just done for you?
Vaccination.
That's a vaccine. Exactly what it is. It's a vaccine. I've given you just enough so that your body recognizes it. So that if you go out in the world now and somebody coughs in your face and you get this massive dose of virus, your body will respond so quickly that the virus won't get a chance to infect any cells. And you'll destroy it before it gets a chance to make you sick. So giving you a vaccine doesn't mean you won't get the virus. It means that when you do get it, your body will respond so quickly that the virus won't get a chance to make you sick. That's a vaccine, and that's what we're doing. We're taking advantage of the way the immune system works by giving you a memory T cell before you actually get the massive dose of virus. Now, what happened to you? Because some of y'all have gotten flu shots and then got the flu from the shot. How many people has that happened to? Man, I went down, got my flu shot, and damn thing gave me the flu. Okay. When we introduced that tiny bit of virus into your body, it was enough to make you sick because your immune system was suppressed at that time. In other words, your immune response wasn't at 100%. What do I mean by that? You were sick from something else. Your immune system was busy when we introduced the virus to you. You were stressed out about something. Stress suppresses the immune response slightly. So you might have been menstruating at the time you got the flu shot. You might have been stressed out about something in your life, work, relationship, or whatever. That's not the time to be getting a flu shot. Or you were sick from something else. You had a bacterial infection in you somewhere. And as a result, the immune response was slow, and it was enough to make you sick. So those are not the times to be getting your flu vaccines or any vaccines. Is when you're stressed out, menstruating, sick from something else. It's like trying to fight two wars at one time. I used to say, and I still do say this sometimes, the reason that we don't all speak German right now is because Hitler tried to fight 2 wars at one time and lost both. Yeah. If they hadn't started a war with Russia during World War II, if they hadn't brought Russia into that war, we would have lost. They damn near won anyway, fighting millions of Russian people at the same time as fighting the Allies. So the Allies and the Russians weren't cooperating. So it was literally 2 wars at one time. And the Germans, or the Nazis, I won't say Germans, the Nazis lost that war because they tried to fight 2 wars at one time. If you try to fight 2 wars at one time in your body, you're going to end up losing both. The bacteria and the virus will run rampant because your immune system can't handle both of them. Yeah. So that's like having a vaccine when you're already sick from something else. You're trying to fight 2 battles at one time, and you're going to end up losing. So that's why some people will get sick, will get the flu when they have their flu shot. They got it at the wrong time. And it's kind of funny that notice that whenever they ask you if you want your flu shot, it's when you're in the hospital or going to the clinic for something else. They ask me that all the time. Oh, you want to get your flu shot today? Lady, I'm here because I'm sick. Why the hell would I have a flu shot today? It doesn't make sense. And that shows you that people out there don't think this shit through sometimes, or they just don't know. Don't have a flu shot when you're sick from something else. You're going to get the flu if you do. So those are our 5 white cells. And you might be asked what type of white cell is responsible for destroying viruses, which type of white cell is or T cell is responsible for destroying infected cells, and so on. The type of T cell that's responsible for turning off the immune system, or the type of T cell that's responsible for remembering previous infections, your T cells. And that's the first type of lymphocyte, is the T cell. The second type of lymphocyte is called a B cell. The B lymphocyte creates antibodies for us. That's what it does. So when we use that word antibody, that's where they come from, our B cells. So right now they are looking at treating the coronavirus with monoclonal antibodies. What are they doing? They're stimulating your B cells in your body to create antibodies against the coronavirus without you actually having the virus. So that's their approach right now. And one approach is to stimulate your body to create COVID-19 antibodies, even though you've never had the virus. That's monoclonal antibodies. So they're stimulating the B cells in people, trying to get them to produce antibodies. So that's what the B cells do for us. They create antibodies. But they also cause allergies. This is why you can't be allergic to something until you've been exposed at least once. You've got to have that thing in your body one time. On that first time, you're going to create this memory B cell right there. Once that's created, you'll be allergic to the thing from now on. That's the rule of allergies. You can't be allergic till you've been exposed at least once. You won't be allergic until that memory B cell is created. Once it is, you're allergic from now on. So that's why you can't be allergic to something on the first exposure. You don't have this right here yet. So the first time you get stung by a bee, you're going to create this. The next bee sting, full-blown allergic reaction. All right. So why do we create B cells against things? We have no idea. There's no way to tell why when I get stung by a bee, my body doesn't create a B cell for it. But when you get stung, your body creates a B cell. And now you're allergic to bee stings, but I'm not. We don't know why that is. Allergies are typically referred to as an overreaction of the immune system. The immune system is responding to something that it shouldn't, like peanuts or bee sting. Once you create a B cell for it, you're allergic to it from now on. Now, what are the 3 categories of allergies that will kill people? We know, like my wife's allergic to pollen and that type of stuff. It's annoying, it's irritating to the body, but it won't kill you. What 3 categories of allergies will kill people if they're exposed to the stuff? What do y'all think?
Peanut allergies.
All right, peanuts. That qualifies as food allergies. What are the other 2? I just mentioned one.
Medicine.
Medication allergies. And the third one? Venom, like bee stings. These 3 right here will kill you, or can kill you, if we don't treat you well. Now, does anybody have a food allergy? The thing is, guys, if I had a food allergy, I probably would not eat at restaurants and that type of stuff. Because even though they tell you that there's none of this in what you ordered, it might have been fixed on the grill next to something that did have it in there. And it only takes that much. How much bee venom is actually put in your body when a bee stings you? It's a drop. Remember, bees are only that freaking big. So whatever's getting in you is smaller than the bee. It's just a drop, and that's enough to kill somebody. So imagine if they're fixing your food on the grill right next to something that does contain peanuts, and you get just enough of that into your food. There you go. It doesn't take much. Can you develop allergies later in life? Yep. I've stopped eating peanuts. The last time I had something with peanuts in it, it made my ears itch. Oh, hell no. Why the ears? The basophils are released in that area. If you're itching, because basophils are active right there. If you eat something and your throat or your ears start to itch right after eating that, stay away from that stuff from now on. There were basophils activated in that area. And why were they activated? And the only reason is for an allergy. Why would your ears itch? Remember, your throat and your ears are connected. So if you get something in your mouth that makes your throat itch, it'll probably make your ears itch as well. And the last time I ate peanuts, I got like a really itching going on in my ears. And I thought, not stay away from them peanuts, man. So I won't eat peanuts anymore, or anything that contains them. So I was sitting up in the instructor room over at Southern Careers, and a little break room for the instructors. It's kind of tradition to have a table in the middle of the break room. That's been in every school I've ever worked at. Always a table right in the middle of the teacher's break room, and people could bring stuff in, set it on that table, and that just kind of lets everybody know that I brought this in for everybody. So if you bring in donuts, you set them in the middle of the table. Everybody knows the donuts are for go and take a donut type thing. But one day I was sitting up in the break room, and one of the admissions reps walks in, and she goes over to this cake that was sitting in the middle of the table. Oh, look, somebody brought cake. And she cuts a big old piece of cake, and she's got it, and she's just chomping down on it. And she goes to walk out, and she stops and turns around and goes, there aren't any peanuts in this, are there? Because I'm allergic to peanuts. See, I hope there are peanuts in there. Your silly ass has a food allergy, and you walked in and grabbed some food. You have no idea where it came from or what's in it, and going to chomp it down like it's free. Yeah, I hope it does have peanuts in it. Guys, if I have a food allergy, I am going to be very, very diligent about checking what's in something before I go biting into it. She grabs this big old and just starts chowing down on it and then says, ooh, oh, there's no peanuts in this because I'm allergic to peanuts. Yeah, I hope your silly ass has a reaction. Anyway, so that's what our B lymphocyte does for us. It creates antibodies and then causes allergies in people. So those are our two types of lymphocytes, the T cell and the B cell. And that gives us our 5 white cells. The neutrophils, eosinophils, basophils, monocytes, and then lymphocytes. The two types of lymphocytes are the T cell and the B cell. And remember, there are 5 types of T cells, all of our white cells, and how they provide immunity for us. All right. So that's the second formed element. We've done the red cells and we've done the white cells. What's this? No, that link doesn't work anymore. Anyway, I'm not going to worry about that. All right. The next formed element is called a thrombocyte or platelet. Thrombocytes form blood clots for us. Thrombo means blood clot. Cyto is cell. The thrombocytes, they form blood clots. Now, how do they do that? All right. Let's look at a blood vessel. With blood flowing through there, carrying all of these cells for us. And then somebody cuts you. Blood's going to start to leak out that cut, either outside the body or inside the body, but the blood is leaving that blood vessel. Now, that cut is going to cause turbulence as blood is leaving through there, but it also is going to cause a rough surface in there. The tissue has been torn right there. So you're going to have a rough surface. So as the thrombocytes flow through here, when they encounter a rough surface, they stick to it and then release strings. They're called spindles, but that's not real important. But what they're going to form is a net that catch other platelets, who will also release spindles that will catch other platelets. And you see what just happened? That cut is blocked by the platelets. Now, once the flow stops through there, these platelets are going to start to pull their strings back in, pulling the platelets closer together to each other. And that's going to pull the edges of the cut closer together. And actually pull it off to where it's clotted off and nothing else is flowing through there now. So that's what blood clots do. They stick together in the area of the cut and block it off. And in this illustration, you can see the net. See how the net is not just catching platelets, it's catching blood cells and everything. And it's closing off the cut right there. So the hemorrhage or breaking a blood vessel causes a rough surface. The clotting proteins, we mentioned that in the plasma. The clotting proteins will allow the platelets to stick together. They release the spindles that catches other platelets and cells. And next thing you know, the clot is, or the cut is clotted off, it's not bleeding anymore. All right. So that's how blood clots happen. In the blood vessel, platelets encounter a rough surface, they start sticking together, clotting off the area so that the tissue can now heal right there. Once everything is healed and closed up, these platelets then break away. And the problem now is that you have blood clots floating through the bloodstream. And what do you think would happen if that gets to a narrowed spot in the blood vessel. Boom. Now what's going to happen? Blood flow to the other side is cut off, is blocked by a platelet that left here, or a blood clot that left the cut and didn't break up, and it gets stuck in a deeper part of the vessel. How many of y'all had babies? Raise your hand. Who the hoochies? Come on, show us who you are. Okay, there go all the hoochie mamas, all them babies out there. All right. And when you had your baby, maybe an hour or two after delivering the baby, that annoying ass nurse came in your room, told you you need to get up, you need to move around, you need to get out of bed. What was that all about? How many blood clots you think is going to take to close off all those blood vessels that ruptured during the delivery? And those blood clots are going to be huge. And if they break off and get caught in your legs, that's called a deep vein thrombosis. Abnormal clot. Deep vein thrombosis, or DVTs, in the legs. If you get up and move around, then as you move the legs, the muscles squeeze against the blood vessels, and they squeeze up these blood clots in there. So getting up and walking prevents DVTs. And it's not just delivery, it's any surgery that you have. We're going to try to get you up out of bed, get you moving around. Is one of the things that the PCTs will get involved in. Go down.
So what's the shot they give you? So when I had my accident, they gave me a shot in my stomach to prevent blood clots.
Okay. We'll talk about that here in just a second. Okay.
Oh.
All right. So, because there are other things that break up blood clots. Right. So, but that's why we want you getting up, moving around, is to prevent these blood clots from getting caught in blood vessels like that, especially the blood vessels of the legs. So when you go on a surgery ward or an OB ward, you'll see these big signs on the wall, or labor and delivery, excuse me. You see these big signs on the wall that say, prevent DVT, get up, move around, reminding the staff there to get in these patients' rooms and get them up out of bed, get them up moving around so they don't have a DVT. Okay. So that's an abnormal blood clot. It happens in a place where it's not needed. And all it does is block circulation in there. All right. So abnormal clotting leads to heart attacks, strokes, deep vein thrombosis, or pulmonary embolism. You see one happening here. See this building up in the blood vessel right there? That's what we call plaque, building up in the vessel. You may have heard of it as hardening of the arteries. You're building up a lot of plaque in there. And as a result, a blood clot gets caught on that plaque and cuts off circulation to the distal side. So if you have a lot of plaque in your blood vessels, it's going to lead to, or can lead to, heart attack, stroke, deep vein thrombosis, or pulmonary embolism, a blood clot getting caught on that. Remember that blood clots stick to a rough surface. And I know in this illustration, that looks smooth right there, but actually that should be illustrated kind of like this. And as the blood flows through there, the blood clot gets caught on that, sticks to it, and there you go. No blood flow to the other side. All right. So that's the danger of abnormal clotting. Cut off circulation to the heart, cut off circulation to the brain, to the legs, or to your lungs. These three, or any one of these, could actually be fatal. And the most fatal of these is the pulmonary embolism. You get a blockage in your lungs. Now, I've had both heart attacks and strokes, caused primarily by, or all of them were caused by either plaque in the blood vessel, causing an abnormal clot right there, or just a blood clot that builds up in an area. Either way, leading to these things. All right, so what do we do to prevent abnormal clotting? Well, we're going to take antiplatelet drugs. These are medications that prevent the platelets from sticking together. And that includes aspirin and other drugs like Plavix. I take both. I was on aspirin for years until I had a stroke. And the doctor said, okay, I had a stroke while I was taking aspirin. Damn, we need to put you on some more shit. And I went from aspirin to aspirin and Plavix together. I take them both. All to keep from getting those blood clots in there like that. Okay. So, and tomorrow when we do the heart, we'll be talking about heart attacks and how they happen. But that's why people go on aspirin as a regimen, to prevent abnormal clotting in the body. Not only that, but it busts up blood clots. Y'all remember yesterday I mentioned a stroke? I had a blood clot in a brain vessel. So what did I do? As soon as I realized I was having a stroke, y'all remember what I did?
Took aspirin and drove to the emergency room.
Hey, aspirin. Yep. And by the time the doctor came in to see me, the aspirin had already broken up that blood clot. And that's what I mean when I say, if you think somebody's having a stroke, give them aspirin, man. Now strokes can also be caused by plaque just completely blocking the vessel. In that case, the aspirin's not going to help them, but it's not going to hurt them either. So you think somebody's having a stroke or a heart attack, if they're conscious and can swallow, give them aspirin, man. It could stop their heart attack or their stroke. And at the very least, it's not going to hurt them. So go on and give them aspirin if they can take it. Now,
What if they've already taken nitrogen or something like that that stops a heart attack? Can you still give them the aspirin?
okay.
Yeah, that
What
works.
you're using is nitroglycerin. Okay, what does nitroglycerin do? If you have a blood clot right here or plaque buildup, either one, what is nitroglycerin going to do for you? It's going to make the blood vessel dilate or open up wider so you can get blood flow around that. So that's what the nitro tabs do. And no, they do not interact with each other. So if somebody's taking nitro, yeah, they can take a couple aspirin on top of that. It's not going to hurt anything. So nitroglycerin dilates the blood vessels. And it's not the same nitroglycerin. So doctor puts a patient on nitroglycerin. He takes it home, tells his family, yeah, doctor put me on nitro. So now they're taking the bottle and they are like very careful with the bottle. You got to be careful with that. Don't drop it or it might explode. No, it's a different type of nitroglycerin. Y'all, it's not the same thing. But there are people out there who will tell you, man, don't drop that bottle, it might blow up. No, that's not the nitroglycerin we're giving you, y'all. It's the same name, but different thing altogether. So what it does is it dilates blood vessels so that even with plaque or a blood clot in there, it makes the blood vessel wider so that the blood can still flow around like that. So that's what nitro does. And no, aspirin doesn't interfere with nitroglycerin and nitro doesn't interfere with aspirin. So you can take the two together. And again, I take aspirin and Plavix together. Now, some people mistakenly call these two blood thinners, but they're not. They're antiplatelet drugs. You see, we don't get in the habit of thinning people's blood because that contributes to your blood pressure. 4 things that contribute to your blood pressure: the contraction of the heart, the diameter of your blood vessels, the amount of blood in your body, and the thickness or viscosity of the blood. If we make the blood thin, it's going to bottom out your blood pressure. And you're going to get lightheaded when you stand up and that type of stuff. So we don't get in the habit of thinning people's blood, but in some cases, some people are to the point where aspirin and Plavix just won't do it for them anymore. And we do literally need to go in and thin their blood. And that's when we start putting you on the blood thinners. All right. So eventually, when these two aren't effective for me anymore, as I get older, I'll eventually be put on blood thinners. Once somebody's put on a blood thinner, that's when they're going to get that bracelet that says fall risk. And they don't want you standing up without somebody there with you. It's called up with assistance. And PCTs, you'll become very familiar with that assessment. You are up ad lib. You can get up anytime you want by yourself, or you're up with assistance. In other words, don't get out this bed without somebody standing there next to you, because those people are on blood thinners. And as soon as they stand up, they'll get lightheaded and fall down. So know what your patient's activity levels are. Are they up ad lib, up with assistance, or are they bedridden? Doctor doesn't want them to get up at all. Okay, now I'm going to ask y'all a question that sounds a little bit off topic, but not. Have y'all ever heard that cigarettes contain rat poison? How many of y'all have ever heard that before? You know,
Isn't it the chemical?
Yeah,
The same chemical?
Yeah, you know, cigarettes got rat poison in them, right? Have you ever heard that?
Yeah.
Guess what? That's true. They do. Cigarettes have rat poison in them.
And ammonia.
Okay. Now, saying that, would you be surprised to know that rat poison is not poisonous to people? That's why we call it rat poison. Now, there are some poisons out there that we use for rats that are also poisonous to people, like arsenic. But rat poison itself is not poisonous to humans. Now, how did we find that out? A baby, 18 months old, sitting on the floor, ate an entire package of rat poison. This happened in the 70s. Remember that little wedge? You ever seen that little wedge? You tear it open, a little cardboard wedge, you tear it open, and there's those green or blue pellets in there, and you put it out for the rats. This kid sat on the floor and ate a whole package of that. Mama came in and saw the package was empty. The kid had blue all around the mouth, and her tongue was all blue and all that, and rushed the baby into the emergency room. My baby just ate a whole package of rat poison. And they're checking the baby, examining the baby. The baby's like, what? The only people panicking in the room were the doctors and the parents. The baby was just like, what? Mm-hmm. They started suspecting that the mother had taken the poison and rubbed it on the baby's face like that, and then rushed them into the emergency room, exhibiting what symptoms or what signs? Remember what we called it? Munchausen syndrome by proxy. I think the mama just kind of faking right here. The baby, like what? Until the technician who was drawing the baby's blood for all the lab samples that the doctor kept asking for. Well, let's get a sample of this. Let's check this level and check that level and so on. The technician that was drawing the blood finally came in and told Doc, I've got the blood samples, but this baby will not stop bleeding. When you draw blood from a site, that site should be clotted off in about 5 minutes. They're 20 minutes down the road and the blood is still running out of the site. And the technician, Doc, the baby will not stop bleeding. Rat poison is a blood thinner in humans. And guess what? They didn't even change the name. They just started giving it to people. There's this one right here. Coumadin. The actual name was Coumadin rat poison. So they just started giving it to people. So when they say to you that, you know, cigarettes contain rat poison, you can just turn around and tell them, well, yeah, we prescribe rat poison to people all the time. Matter of fact, it's one of the most prescribed drugs in the United States. So we give rat poison to people all the time. It's called Coumadin. Didn't even change the name. It was Coumadin rat poison. Now it's Coumadin, the medication. Now, once you go on heparin, yeah, fall risk, bruise easy, that kind of stuff. But man, if they put you on Coumadin, that's it, y'all. That you won't even be able to stand up for 5 minutes. That's like sit up on the side of the bed, let your feet dangle on the floor, and just sit there. Do not stand up. You will fall down. That's how thin your blood is. So yes, we put people on rat poison all the time. We just call it Coumadin. It's one of the most prescribed drugs in the United States, Coumadin. All right, so anyway, I'll eventually end up in both of these. If I have another stroke or a heart attack, taking both of these, you need to be on heparin. It's the same heparin that the basophils release, by the way, that thins your blood for you. And then when that gets to not working very well, on to the Coumadin, if I live that long. So that's the difference between antiplatelet drugs and blood thinners. These prevent the platelets from sticking together. These actually change the viscosity of your blood and make it thinner, more like water. All right. So those are your thrombocytes, and that gives us all of the formed elements of the blood, the red cells, the white cells, and the platelets, and what each one does for us. All right. We've talked about abnormal clotting, and we've also talked about the hemorrhage and how our body handles that by creating blood clots in there. So quick review. The formed elements, know them. The red cells, the white cells, and the platelets are components of blood, the formed elements, the plasma, and the serum. Know that plasma contains clotting proteins, and that our blood cells are known collectively as formed elements. Actually, this part down here should not be read. Okay, so our blood cells are known as formed elements, and plasma contains the clotting proteins, the thing that help our platelets stick together. Know the formed elements and their nicknames. Which formed element is nicknamed red blood cell? And you'll choose erythrocyte. Leukocytes are the white cells, and thrombocytes are the platelets. Old red blood cells are destroyed in the spleen. After a red cell is destroyed, the heme and iron are stored in the liver. Oxygen molecules bond to the iron of the heme. A decrease in red cells is called anemia, and the most common form of anemia is iron deficient. O negative is a universal donor. AB positive is the universal recipient. The 5 types of white cells and what they do. Name the white cell that is responsible for destroying bacteria. Name the white cell that's responsible for destroying allergens and parasites. And by the way, I want to stop here for just a second because of a condition out there that's being touted in the news today. Is called eosinophilic asthma. You see, if the allergen is getting into your lungs, you're going to have a shitload of eosinophils rushing to your lungs. And that's going to block up your respiratory passages. You're going to have eosinophilic asthma. You have too many eosinophils in your lungs. And they're going to treat you with a medication that keeps the eosinophils from getting to your lungs like that. So these can actually cause problems in people when they rush into the lungs to destroy any allergens that you're breathing in. And you end up with eosinophilic asthma, too many eosinophils in your lungs at one time. So eosinophils destroy allergens and parasites. Basophils are responsible for the symptoms of allergies. the 5 types of T cells. And then, don't ask any questions about platelets. Yes, I do. I know I do. The blood cell that's responsible for forming blood clots or your thrombocytes. Okay. And as soon as we're done, I'll re-email this out with the new reds and stuff in there. Matter of fact, let me just take this one out of here because I don't use it anymore. Anything else? Okay. And that's hematology, your blood and blood cells. All right. So again, let me go on and send this now. So save it, close it down here. New message to all of y'all. Dated hematology PowerPoint, attached from the cloud. There it is right there. Okay, and go on and send that. All right, so that is your updated PowerPoint for hematology. It's 5 minutes to 12. We're going to go on and finish for today. Again, now would be a good time to get in and get some of that homework done. Remember that the neurology and psychiatry test is up there. You can go on and study for that or take it if you're ready. I sent out that email this morning with those names on there for those people who need to take those tests, the intro and the gastro test. The review is there and the links for both tests are there. If your name's in that list, it tells you which one you haven't taken yet. You need to go in there and get those done. They'll be activated until, I think, noon on Friday or something like that. But get in there and get those done as well. You cannot have a 0 on your grade sheet. You got to get those done. Even if you only scored 30, is better than 0 on your grade sheet. So get in there and get those bad boys done, and that's what we'll do for the last hour. Study, do your homework, take tests if you're ready for them, and then we'll continue the lecture tomorrow morning at 8 o'clock. I'll keep the class open so that if there are any questions, again, you can just speak up. I'll hear you come in here and answer the questions that you have. So if there's any questions before we